coroutines tutorial. It's a little hard to believe. Just out of curiosity, how many people have done anything with Python's coroutine feature? Nobody at all. Okay, one person. This is good. It'll put everybody on equal footing for having their brain like melted down about halfway through. So I'd just like to welcome everyone to the coroutines tutorial. I'm Dave, if you haven't figured that out. So what this tutorial is about, not to sort of beat around the bush about it, it's basically a very extreme tutorial on coroutines. I sort of looked up the definition of mondo in a couple of places, and it's like extreme in nature, and then there was this other definition that sort of emphasized extremely rapid. So this sort of has both qualities kind of in the tutorial. So you might want to brace yourself a little bit. As far as the requirements of this class, there's no third-party modules whatsoever. You basically just need Python 2.5 or newer. Probably not Python 3 because some of the examples I haven't gone through and taken care to fix all the print statements or anything like that. But in principle, it will work on Python 3. There's a website where you can download all the code. For those of you in the back, you might want to download that. Might be a little bit more readable than what's up on the screen. I do indicate file names as needed. As far as a high-level overview of what this class is about, it's mainly kind of focused on addressing maybe a gap in documentation, if you will. It's basically, we're going to look at sort of what is a coroutine and what do you actually use them for. I mean, I'm trying to fill in basically some pieces about what this feature of Python is about and actually give some practical motivation for using it. And sort of a pictorial overview of how this tutorial sort of plays out is for the first half or so, I hope it kind of builds up gradually. And then in the last half, we're actually going to write a multitasking operating system with no threads or subprocesses. I don't think that section quite approaches the level of meta classes, perhaps, but it's kind of in the same ballpark of the sort of killer joke aspect of it. Another thing that I'll just mention about the class, it is possible that we may not cover all the slides in the time allotted. I think it might be possible, but there might be a jump at the end. So this may be a tutorial where you have something to look at on the plane on the way back. I don't think that will diminish what we're going to do, but just be aware of that. Okay, so a little bit about me. Been in the Python world quite a while. You may know me as the author of the Essential Reference book, and just as a shameless plug, a new version of that is coming out in like 2 months. So you can go buy several dozen copies for your friends. I also have created some packages like Swig and Ply and things of that nature. And some other background, if you went to my generators tutorial last year, or you saw that online or someplace like that, you'll know that I'm a pretty big fan of generators and generator expressions. So I gave this basically insane tutorial last year with just tons and tons of generator examples. This tutorial, in a way, is kind of a sequel to that, if you will. And so what we're going to really focus on in this tutorial is actually this coroutine feature of Python. If you weren't paying close attention, one of the things that Python 2.5 picked up was this sort of magic send method that would let you just sort of send values into a generator. And this is the so-called PEP 342, if you go look for that. Basically, it's a description of this sort of some advanced or enhanced generator features. And if you try to find out information on that, it's a little bit bizarre. I mean, there's like not a lot of examples on it, and some of the books covering this are, they kind of brush on the topic, but don't really delve into it in great detail. I don't want to pick on book authors too much, but this is a typical excerpt. This is actually from a very recent Python book. And it's actually a great book, so I don't want to pick on the book specifically, but this is basically the entire extent of the description of coroutines. I mean, basically the book says, well, yeah, there's this feature that you can do this thing with generators, and it's useful for threads and things like that, and oh, go look at PyPy. So it's sort of a complete sort of punt, if you will, on sort of what this feature is about. And then there's sort of this other problem that if you actually do go to PyPy and try to look at what people are using coroutines for, you might get sort of this description. It's a little bit whimsical, but you'll get some typical description, where it's like it's all really simple, and then you have, the toelet and the footlet and the anklet, and like pretty soon, like your head is sort of swimming in some very, complicated, convoluted description of how coroutines are cool. And I think my brain is just too small to wrap my brain around that, or kind of understand that, if you will. So. So what we're going to do here is actually try to kind of fill in that gap a little bit. And just as some disclaimers, what I'm going to talk about, is essentially coroutines, which, if it's not the most obscure feature, it's definitely in the running for that prize. And then we're going to mix in sort of concurrency, which is probably the most difficult topic in computer science, usually best avoided. So we're going to sort of take these two things. I'm hoping that it doesn't create some sort of mushroom cloud, or hope nobody dies in the process. But that's kind of what we're doing here. The other thing that I guess I would mention is that I learned to program in the early 80s and 90s and so forth. I've actually never used a programming language that had coroutines. Now, that's not to say that languages didn't exist that had them. I think I read somewhere Modula 2 might have had them, and in a few other languages. But this is a feature that you just don't see in a lot of programming languages of that era. And if you actually do, kind of look at the history of them, they actually go back pretty far. I mean, it's sort of coroutines. A lot of the work on that sort of happened in the 60s and 70s, and then it sort of morphed over into some other things like programming with threads, continuations, things of that nature. And I'm actually kind of interested as to why coroutines, this feature that's 50 years old, is all of a sudden showing up in all these scripting languages. I think that's kind of interesting that has happened. So that's part of what we're doing here. Another disclaimer is that I'm completely a neutral party on this. I'm not promoting any libraries or frameworks that I've created. I didn't have anything to do with that PEP 342. So, nothing to do with that. Not particularly religious about this. I would say, if anything, I'm a little bit skeptical about this whole coroutine business. And that's kind of part of why I'm teaching this, is to really just explore the space and sort of see what it's all about. And then the final disclaimers. This is not meant to be an academic presentation on coroutines. I mean, we could go down a certain direction with this that would just be, tons of programming language theory and looking at prior art. Not going to do that. There's not going to be any proofs. There's not going to be any Fibonacci numbers. I mean, mainly the focus here is on practical things that you can do with this. Just in the interest of full disclaimer, I do present some performance numbers in the notes, and this is here just to tell you what I ran those on. So not so interesting, but just for future reference, that's what I was using. So what we're going to do here in part one is I'm going to kind of give you the gentle introduction to some of this stuff, and then we're just going to build on it as we go. I do want to encourage people to ask questions at any time. Just raise your hand. We'll go into that. Because of the big room, I'll try to repeat the question so people can hear it. Again, I do encourage people to follow along in the code samples. I'm going to be looking at a lot of code and kind of explaining it. And so forth. So to start the class off, I am hoping that people have probably seen generator functions at some point or another. This is sort of a simple example of a generator. Basically, it's a function countdown that essentially just spits out a bunch of numbers one after the other. If you have not seen something like this before, generator is a very different kind of function than what you normally encounter in Python. Essentially what happens is if you call one of these generator functions that uses the yield statement, what you'll find is it doesn't actually do anything. It's a little mysterious. You basically call it, and you won't see any output or anything of that nature going on. And what has happened with a generator is that when you call that, you basically launch a function, but it kind of starts up in a suspended execution state, if you will. So you've sort of initiated it, but you actually haven't done anything with it. And the way that you use it is essentially executing next operations on it. So what happens is when you create a generator, you call next, and it basically gets the function to run, and it will do that until it hits that yield statement, in which case a value pops out of it. So that sort of process of basically launching the function and hitting next, is sort of how you get a generator function to execute. And that execution model sort of continues until the generator function falls off the end of its execution, in which case you get one of these sort of stop iteration exceptions. And so usually the whole point of this is it really is kind of a way of creating a type of iterator in Python. Just as kind of an example of that, let me go over to idle here. If you were just sort of to load up, this is sort of a simple, the simple generator that I defined here. The way that it typically gets used is to hook up to the for loop like that. So if you were to run this, what's happening is this for loop is essentially calling next on the generator function, and the generator, this yield statement is basically popping out values to use in the for loop. Now, as a practical example of that, I'm not going to repeat everything that I did at last year's tutorials. I'll just say, if you have not seen this before, I would strongly recommend looking at maybe the generator tricks tutorial to see how this is used. But I think a major powerful feature of generators is that you can actually set up pipelines. So if you've used things like Unix pipes or anything of that nature, one of the cool things about generator functions is that you can actually chain them together and create these sort of processing pipes. And just as an example of that, I have in the notes sort of an example of implementing the Unix tail -f command. If you know anything about log files or anything like that, that's a command that a lot of Unix programmers will use to maybe like monitor a log off of a server or something. Well, actually, I guess it helps if I go into the right directory here. So essentially what somebody could do is they could say, tail -f access log, and you sort of see things being written onto a log file. It turns out that if you wanted to implement that in Python, you can actually do it with a generator function. So as just an example of what that might look like, I'm going to pull it up in idle here. There's this example follow, which is essentially a Python implementation of that tail -f feature in Python. And what this is doing, I'll sort of explain the steps. It's essentially taking a file that you pass it, and then it's seeking to the end of the file. That's actually what this seek operation is doing. And then what it's doing is it's just essentially sitting there at the end of the file, just constantly readlining, basically saying, do you have any new data? Do you have any new data? Do you have any new data? And it essentially just does that forever. And what happens if any new data shows up, I just spit it out with this yield statement at the end there. So I don't know that you can see the cursor, but the highlighting in idle seems to be a little disabled at the moment. But the way that something like that would work, it's actually kind of cool. What you can do is you can essentially say, okay, open up some log file, and then you can just do like a for loop. You can say for line and follow this log file, and you've got all this sort of processing going on behind the scenes of that. So if you run that, all of a sudden you're sort of following that log file kind of the same way that you did in with the Unix tail -f command. So that's sort of one sort of cool things with generators is that you can actually implement these really interesting sort of iteration patterns like that. And then the other thing that you can do with generators, and this is more of the pipelining idea, is that you can actually stack generators together and set up these sort of processing pipes. Basically what you can do that is you just create a whole series of generator functions and you kind of layer them on top of each other and pull data through this processing pipe with a for loop. I'm going to show you an example of that. One way that you can do that is, this is sort of maybe the lamest version of the grep command that's ever been created, but here's another generator function that essentially loops over a bunch of lines, and then it just uses the in operator of strings to basically say if this pattern is in a line, I'll yield it. And so what somebody might do with this is essentially they would maybe open up a log file. They would then do this follow operation on it, which is, again, that's the Unix tail minus F. And then what they would do is feed the log file into this grep function. And essentially what you're doing is kind of stacking things up and doing a little bit of a filter. So just as some example code of that, there's this pipeline.py function, which essentially does that. So I'm kind of using that follow thing that I did just now, and now I'm hooking it up to this this grep thing, this grep function, and then I'm printing out the lines. So if I were to run this, what you're going to have is basically Python reading all the lines off the end of this log file, feeding them into this grep function, and then printing out the results. Okay, so if you run that, it's not going to print as much data because it's looking for a very specific pattern, basically looking for the word Python. But if you kind of look at the output, you'll see Python in sort of every single line that comes out. So those are some of the things that you can do with generator functions. Let me just pause for a minute and ask if anybody has any questions about anything that's happened there. Admittedly, that's a pretty fast example, but the generator talk from last year actually has a lot more examples of that. It's actually a small taste of what you can do with things like generator expressions and generators and so forth. Basically, you can set up these very long processing pipelines where you do different kinds of processing stages. You can have all sorts of like interchangeable program components for doing sort of Unix sort of pipe-like stuff. So that's sort of a taste of that. And again, just to kind of look at the code, what's happening. We have this one generator that's kind of spitting out lines coming off of that log file. And then we wrote this, this grep function where, that's basically taking those lines and kind of filtering them a little bit. Okay, so that's kind of a taste of generators. Now, the reason why I've gone through this kind of fast is that this class is not really about generators. The course is sort of billed as a course on coroutines. So what in the world is a coroutine? So let me kind of get into this, and we'll take this in a little bit more detail. Basically what happened in Python 2.5 is that the behavior of that yield statement got sort of re-envisioned a little bit, if you will. And the ability to use yield as an expression in a statement was added to Python. And basically what that means is that you could stick the yield statement over on the right side of an equal sign. So you could say things like line equals yield. If you do that, you get a very different sort of function in terms of what happens here. So let me just type up that example and look at it a little bit sort of piece by piece. Okay, so we're done with the pipeline here. So what I'm going to do is I'm actually going to write that grep function that I had before, and it's going to look a little bit funny the first time you see it. So I'm going to put a print statement in here looking for pattern. I'm going to do a while loop, and then I'm going to do this funny thing with the yield statement where I say line equals yield. And then I'll, if the pattern is in the line, I'll print that out. if you create a function like that, it becomes, it actually behaves in kind of the same way as a generator. I mean, basically, I can say g equals grep Python, and if you look at it, it comes back saying, well, this is some kind of generator function. But it's a little bit weird in sort of looking at that. You're saying, well, how exactly is that supposed to work? I mean, first of all, sort of what is the value of this yield statement on the right side of an equal sign? And then what's the deal with yield not spitting out a value? I mean, one of the things with generators is that yield is always producing values for loops. This is sort of not doing that, and it's got yield kind of flipped around in an unusual placement there. So if you create a function like this, the way that it works is actually kind of the inverse of a generator that's used with the for loop. The way that it works is that essentially you have to start it up by calling next. So you would essentially say next to get it to run. And what that has done is it's essentially advanced the code to this yield, at which point it's suspended. And then what you do with the function at this point is instead of having it produce values, you actually send values into it. And this is sort of the key difference between, say, a normal generator function and what a coroutine is about. So the way that this is meant to work is that you essentially send the function data. So you do this send operation where you can essentially just send input values into it. And it turns out that these values that I'm sending in are actually what are coming back from that yield statement. So if I were to send in a line that had the word Python in it, all of a sudden you see it printed out. I mean, essentially what happened is this code here received that line and it said, oh, Python was in that line. I'm going to print it out. So it's kind of interesting. You essentially have this function that's just kind of always sort of suspended, if you will, and it essentially only runs in response to data that you send into it. So you can essentially keep it alive as long as you want, and it's if it happens to match some line that contains what you're looking for, it will sort of print it out. So is everyone with me so far on that? Key point, coroutine is something that you send values into, not hooking it up to the for loop here.
Within idle, what do you have to do to stop that?
Okay, so the question is, within idle, how do I stop it? One way to do it would be just to restart idle. The other way to do it, you could just delete it. Like if you just said delete del G, it would just delete the coroutine and it's gone at that point. If you don't do anything, the coroutine, it actually just stays active basically indefinitely until it's either garbage collected or sort of shut down. Yeah.
Could you throw an exception at it?
Yes, so let me fill in a couple of details. So Wesley just asked if you could throw an exception inside of a coroutine. So let me kind of fill in a couple of details. You might look at this and say, well, this is pretty weird. So you essentially have this this yield on the right. And so again, the key idea with the coroutine is that you're sending in values to this function. A couple of the slides here are just kind of emphasizing the execution model. Runs in kind of the same way as a generator. Basically, if you call it, nothing happens. In order to get it to run, you basically have to call next and send methods on it. There is one little oddity I need to mention. One aspect of coroutines is that in order to get them to actually work correctly, you actually have to get them to advance to the yield statement. And this is a little bit odd, but one of the things that you saw me do in my example is that you essentially saw me do this, okay, G equals grep Python, and then I had to do this next business. What that is essentially doing is getting this to advance to the yield. And if you forget to do that, so let me I'll do this to start a flame war, but let's say you were, looking for Ruby or something like that. If you tried to send in, some text without calling that, okay, we'll really start a flame war here. If you were trying to send in, something without calling that next, you end up getting a type error in Python saying you actually haven't started the generator yet. And basically it hasn't reached a point where it can receive a value. So one thing that's a little bit tricky with these coroutines is that you essentially always have to ping them with this next operation to get them to go to the first yield where you can actually send them something. So I want to mention one little trick that can be done to do this. If you see people messing around with coroutines, it's pretty common to see them wrapped with a decorator function. And what this decorator does, hopefully people have seen decorators one time in their life before, but what this is doing is it basically wraps the coroutine with a function that basically will start it and then automatically fire the next on it. When you first call it. So what's happening here is this bit of code here is essentially launching the coroutine, you ping next on it, and then it essentially takes care of that detail automatically. So just as a slight variation, what you tend to see people doing is you'll have this sort of magic coroutine decorator, and what you would do is do something like this, where if you were going to define a coroutine function, well, I just screwed it up there, you would essentially say, well, this is a coroutine called grep, you do the little print, and then you do the usual sort of thing here.
Parentheses around the yield. Is it just?
I think it might actually be required if it's just a bare, like if there's no argument to the yield. I have to check into that, but there have been like some syntactic issues. Does anybody happen to know the answer to that?
I just tested it. The parentheses weren't required.
They weren't required? Okay. Okay. Well, I use them anyway, so bad on me.
At least in 2.6.
It's to emphasize to the user that it is an expression, not a statement.
Okay, yeah, that's actually a good point. What the response is to emphasize that it's an expression, not a statement. I tend to use it with the parentheses in the coroutine kind of code. So a very common thing that you see with coroutines, again with this decorator, that little trick that is in the notes is essentially automatically doing the next operation, because when you work with these, with coroutines, it's often easy to forget that. So what you're seeing here is when I do this grep, it basically already fired the function once to get it to advance. And then it's automatically just sort of primed and sort of ready to go. So I will use that in a couple of the later examples. You'll see me kind of using that. Now, a couple of things that came up earlier. There are some things that you can do with coroutines to be aware of. One is that a coroutine actually does run forever unless it gets garbage collected or destroyed in some way. There is a method on coroutines close that will shut it down. So if you launch a coroutine and then you do this g.close on it, that will basically get it to stop. And it turns out that that actually does something in the coroutine. There is a way to catch that. Essentially, if you put your code in a try except block where you catch this generator exit, that exception gets raised at the yield statement if somebody has closed it. So one of the things that you can do is if you do need to shut down one of these coroutine functions, you can basically catch that and do some kind of cleanup if you want to.
Is it really running?
Or is it like a stopped generator?
It's just a stopped generator. Yeah.
So it's defined taking up space, but it's not running.
Right, right. Well, yeah, one key thing about coroutines, they're not threads or anything like that. When they're stopped, they're not doing anything except taking up memory, basically. And then to answer Wesley's question, he asked me, can you throw an exception inside of a coroutine? There's also a throw method that can be done to do that. Essentially, if you do this g.throw, and then you just give it the exception name and a value, you'll essentially get that same exception originating at the point of the yield statement. So there is a way to kind of, to do those things, and you can catch and handle them in sort of the usual sorts of ways. Now, one little interlude on this. I think one thing to be aware of is that generators and coroutines are kind of doing two separate things. I mean, I think most Python programmers are used to the idea of using a generator to spit stuff out to a for loop. This coroutine business is a little bit different in spirit. I mean, essentially what you're doing with a coroutine is tending to consume values. So, I mean, when you're sending things into one of these coroutine functions, you're not really typically using it in the context of a for loop. And one thing to be aware of is that you really don't want to mix like iteration and sending together. I mean, technically you can, but it kind of is confusing to figure out. This is some code that is, it's basically using a generator to do a countdown, but I basically am using sort of a weird generator expression with the idea that somebody might be able to reset the countdown at some point in the middle. So what happens here is it's almost like you can send in a value like midstream and have it reset. If you play around with this, it's kind of flaky, actually. I mean, I have some sample code in the directory that you can look at. But what happens is this code down in the bottom corner here. This is basically the holy grail countdown that I'm trying to do here. 5, 3, sort of thing like that. If you were to send in, like let's say the count reached 5, and then you sent in 3. What ends up happening is the 3 gets lost somewhere in the middle of the process somewhere. And what you're really seeing there is essentially some kind of flaky execution of this of this generator function. So I would say, just as a general rule, you don't tend to use like generators and quote coroutines kind of at the same time like that. So just to kind of keep your brain from exploding, I would say probably a good idea not to mix the two concepts together in the same function. You obviously can if you want to, but I think it's just asking for sort of trouble down the road. So before I go any further, let me just ask, are there any questions about what's going on there? Question kind of in the back there.
Okay, this is can you and would it be wise to have multiple yield statements or perhaps a conditional that says where to go, which yield to go to?
So the question is, can you have multiple yield statements, maybe in conditionals and so forth? Perfectly fine to do it. In fact, it's actually a really useful thing to do to implement state machines. And we'll see an example of that in a second. Essentially, you can have like a coroutine that sits on one yield statement for a little while, but then if it enters like a different execution state, you could actually have it branch off into some other part of the code that's using a yield at the same time. I think probably that the key thing, if you had multiple yields, though, if you would want to be consistent in what their purpose is. Like if you're sending things in, you would want to continue to send things in as opposed to suddenly flipping around and turning into iteration or something like that. So any other questions before we go on? Okay. Well, what we're going to do here is actually kind of take this idea of having a function that you can send things into, and actually look at some applications of how you can use this. So what I'm going to do is actually start off with the same thing that we did with generators, but I'm going to flip it around a little bit. So one of the things that's kind of interesting with coroutines is that you can actually use them to set up processing pipelines in exactly the same way or same spirit that you did with generator functions and yields and like iteration. And the way that you do that is essentially by just having a bunch of coroutines send data to a successive chain of other coroutines. So as an example of doing that, or how that gets set up, what you need to do to do that is essentially have some kind of function which acts as a data source. So you need to have some function which is basically producing items of some kind. Maybe you're reading them from a file, maybe you're getting them from a database, maybe you're getting them off the network. Doesn't really matter, but this function is essentially going to drive the calculation. Basically, this is getting the initial data, and then what it's going to do is essentially just send it into some target. So this source function is essentially going to take some destination of the data, it will read it, and then you'll just use the send function to send it along. As far as the other component, you need to have some kind of endpoint for this pipeline. So if you are setting up a processing pipe, you typically are not going to create an infinite sequence of processing steps. So this endpoint here is generally going to be some kind of coroutine that just receives values, and then once it's done with them, it doesn't actually send them anywhere else. So you essentially have sort of two elements of your code here. You're going to have some kind of sender, this source function, and you're going to have some kind of sync function which just receives data and then doesn't do any more processing on it. And as an example of that, this is sort of an example that mimics that thing that I did with the tail minus f function kind of earlier in the course. What I've got here, let me pull up the code for that. So I have a function co-follow here. What this is it's a function that almost mimics the same code that I did with the generator function earlier. Essentially what it's doing is it's going out to the end of a file. It's trying to read lines sort of repeatedly. You know, so it's going read line, read line, read line. But instead of using the yield statement to like spit it out to a for loop, it's basically just doing this like send operation at the end where it's saying, well, if I get a line, I'm just going to fire it off somewhere at some target. And to use that, essentially you just have to kind of flip your thinking around a little bit. The way that it works is that this code here, this printer thing, is essentially a coroutine that's going to receive lines sent to it. Okay, so remember when you use the yield on the right side like that, you're receiving data. And the way that you would hook up those two pieces is you would essentially do this thing at the bottom. You would say, I'm going to open up this file. I'm going to follow F. Okay, so you'd say follow F. And then the target of that is that printer function. So it looks a little bit different in terms of how it's kind of hooked up. But you're saying you're going to run this follow thing, and then you're going to target all the data that it gets off onto this printer function. So if you run that, you get the same output that you had before, but it's kind of been, the whole thing has kind of been inverted as to how it operates. Any questions about how that got set up? You know, keep in mind, you know, instead of yielding values out, the whole thing has been flipped around. You're sending values on. So that's kind of an example of setting up a pipe. So we have a question up here in the front.
So in that example there, that printer coroutine, this regards to the garbage collection. When would that be garbage collected in this case?
So the question is, when would this printer thing be garbage collected? Where it would get garbage collected actually is, I mean, essentially we've called it and passed it as an argument into this follow function. It would essentially get garbage collected when the follow function actually completed. So it's basically it ends up being a local variable to that function because I didn't store it in any other variables. So the only reference to it really is this target argument. And so it would get cleaned up when follow terminated. It turns out that follow is set up to run in an infinite loop, so it would actually never get cleaned up in this program, but
But the fact that it's doing the yield, or the yield as an expression doesn't prohibit it from being not garbage collected.
right.
That makes sense.
So yeah, coroutines are definitely garbage collected. So if you create like a printer or something and it just goes out of scope, or that variable gets cleaned up, the coroutine is gone at that point.
Is that similar for generators?
That's the same for generators. So yeah, generators also get cleaned up if they're no longer in scope. One thing on the subject of garbage collection, I don't have a slide on this per se, but I mentioned earlier that you could basically close a coroutine by doing .close. That actually happens automatically if something gets garbage collected. So if you had like a generator that was in a variable and that variable just got collected by the Python garbage collector, close is actually automatically invoked on that. So you'll actually get the generator exception or generator exit firing in the coroutine when that happens. Okay, so we just did kind of an example of a pipe. To kind of take it one step further, you can also start adding like intermediate stages to this. This is where it gets kind of interesting. You can essentially have like a pipeline filter where it both receives and sends values. So this is kind of a slightly, so what's happening here, we have this function that basically receives with the yield, does something to the data that it got, and then sends it along to sort of a further processing stage. So if you wanted to do the same thing as that grepping thing that we did earlier, you could have a function grep here where it's essentially it's receiving lines, and then if the pattern is in the line, instead of just printing it out, you just forward it on to something else. So the way that this would get hooked up is you essentially start stacking these sort of coroutines on top of each other. So I think I have that in a window. Let's see, co-pipe. Okay, so here's kind of an example of that. I mean, essentially, I have the follow function's basically reading lines off of a file, sending them to some target. Here I have a filter which is receiving lines, checking to see whether some pattern is in the line, and then sending it on to some other target. Here I have a printer which is basically just receiving lines and printing them out. And here's sort of an example of hooking it all up. So this code at the bottom, it reads a little, the syntax is a little bit funny looking, but basically it's saying run this follow function, and the target of that is the grep function, and the target of the grep function is the printer function. So it's essentially you've got like all these coroutines starting to stack on top of each other. Very Lispish. Yeah, are you looking at all of the extra parentheses there?
You say that like it's a bad thing.
Yeah. Oh, it's going to get much worse. So.
So you need a reference to your to the next target down the pipeline, or can you be a generator and a coroutine at the same time? Could you just say yield instead of target.send?
You could say. So the question is, can you put a yield without a? I mean, can you like generate values and send values?
Can you accept values like a coroutine, but also yield like a generator?
Oh, okay, yeah. So the question is, can you accept values like a coroutine, but also produce values like a generator?
Right, here instead of saying target.send.
Right. It is possible to have yield also return values. I'm going to get into that in a little bit later. It's a little bit tricky to both receive and return values.
Well, you're doing it
But-
here, you're just doing it with target.send.
Right. Well, maybe I don't understand the.
The question is, where are you suspended?
Oh, where are you suspended?
Yeah, I mean, if you're the coroutine, are you waiting for the send, or are you waiting for the next?
Okay. So the question is, where are you suspended? Coroutines always suspend on the yield.
So you can't be waiting for the next. What would the next do? So
Well, actually, next and send are basically the same. If you do a next, it's the same as sending none.
Okay.
into a generator. So. I've been digging a big hole for myself there. But getting back to the example, hopefully you can sort of see how this is kind of setting up a little processing pipe. And it's throwing in a little bit of very Lisp-ish looking syntax there at the end, mainly just to make people's brain explode, I suppose. But as just kind of an interlude, I mean, if you kind of can wrap your brain around what's happening here, you've essentially taken like this whole generator idea up top where you're pulling things out with a for loop, and you've completely flipped the whole thing around. I mean, it's almost like you've inverted the whole control flow of this thing, where with iteration, you're basically pulling things out of the pipe with a for loop. So all of the program is basically driven by this for loop at the end of the pipe. With coroutines, you're basically focused on the source is where the control is. Basically, with a coroutine, you've got some piece of code that's just pushing data into the processing pipeline, and this is sort of where your program is running. So you can do similar sorts of things, but it's kind of, you've sort of changed, where in your code a lot of the, actually the actual execution is being driven there. Now, one of the things that's a little bit scary with coroutines, because you're essentially driving these processing pipes by pushing data in at the front like that, you actually have the option of branching out. And I'm not sure this is a good thing or not, but it's certainly possible. One of the things that you could imagine is a source that's pushing data into some coroutine, and then all of a sudden the thing just splits off into like a broadcast or something. So here's sort of an example of a broadcaster. I mean, basically this is a coroutine that takes, instead of a target, maybe a list of targets, and then what it does is takes an item and then just sends it to every target. If you were to sort of use that, you could end up getting code like this. So this is basically a code where I'm reading off some access log, but then I'm broadcasting it onto 3 different instances of the grep printer coroutine sequence there. So if you were to look at something like that, I think I have that here. What this is essentially doing is I have 3 different little processing stages. One is looking for Python, one is looking for ply, one is looking for swig. Okay, I'm doing a little bit of self-promotion on that perhaps, but if you were to run that, what you're going to see is this thing is now going to print out lines that kind of match any one of those 3. So there's some Python lines, there's a ply match. It's essentially driving a whole bunch of different components. The syntax for it probably leaves a little bit to be desired. I mean, if you're looking at this, I mean, there's a lot of sort of like connecting pieces sort of going on in that one operation there. Another sort of scary thing that you can do, and I almost hesitate to mention it, is you can even do things like this. This is essentially a variation where I create one printer target, and then I broadcast out onto 3 different coroutines, and then they all take their results and like collapse it back down onto the printer object. So hopefully that one's a little bit more sort of disturbing, perhaps. But the takeaway is that essentially you have these these generator functions where you can start pushing data into them. They can branch out. You can route data around. It's sort of a whole new realm over what you might do with a normal generator function. So questions on that?
Why do you consider that more disturbing?
Well, the reason I consider this so the question is, why is this more disturbing? Personally, I get a little bit worried anytime I have like a fan-in kind of thing like this over at the end. It's like, wait a minute, I have like 3 different sources funneling data into one coroutine. All of a sudden, sorts of questions sort of come up. It's like, well, is that a safe thing to do? Do I have to synchronize that with a lock or something? Or
It's not like they're running at the same time, right?
Right.
Your
So
broadcast is calling them the sequence.
Right. So, so I think there are questions here. It turns out that for coroutines, this is safe because they don't use threads. But one of the things that we're going to get to in a second, if you're looking at this, it's like processing stages, sending things to each other. There's like an angle of like concurrent programming, or like distributed systems and things that you can think of with that, and then that becomes kind of an issue.
Can we guarantee the lines printed by printer are printed in the same order that they were in the log?
I think so, but I don't have I wouldn't have a mathematical proof on it. Yeah, I think they would be actually, because these are not threads, and basically the control flow will sort of work out like that. If two of these things happen to match the same line, they would fire in the same order that they were listed there. So there will be a quiz later, by the way, if your head is spinning on that. Just as another interlude, I think one kind of takeaway on these examples is that there's some pretty interesting kind of data routing possibilities with coroutines. I mean, basically, you can take a whole bunch of little components and kind of glue them together into things like pipes and broadcasts and branches and so forth. There are some limitations of that we'll get to in a bit, but I'm going to defer on them for the moment. One little digression, and I think this is probably going to put me in Python purgatory for at least 6 months. Having written this code, I wish that variable assignment in Python was an expression. I don't know that it's a subtlety, but I wish that I could drop the line equals yield into the while statement. Now I know that there's going to be some knight that's going to come out of the woodwork and bash the hell out of me some point during the conference for even suggesting such an idea. I'm not holding my breath on that, but
it would probably be yield as, just like
so. Let's not even contemplate that. I don't think I'm on Guido's bad side, but I don't want to end up there because of that. Another thing that's a little bit subtle, this coroutine business of sending things in, if you've done any kind of OO programming, I actually think it's kind of similar to what you see with people defining handler objects. I mean, you might not have seen this precise programming interface, but a lot of OO systems kind of have this idea, where you define a handler object that maybe responds to things sent to it, and then you plug the handler into some other piece of the code. You see this a lot with parsing libraries. Another thing, example I can think of is maybe the socket server library in Python. If you've ever used that, you have to, you define a little handler class and you plug it in. And one thing about that, you can actually kind of view coroutines almost as a simplification of that for certain kinds of problems. And one thing that's kind of interesting with coroutines is that you basically take what you might otherwise do with an object and you almost collapse it down into just a function definition. I mean, so you basically have this one function. If you're messing around with a class like that, it's sort of more stuff you have to put there. I mean, basically you need a class definition, you need to define 2 methods. If you're working with classes, you probably have to have a base class, and if you have a base class, it probably means you have to have a library import. And it's like all of a sudden you've got quite a bit of machinery sort of coming in to do that. And so I think coroutines, in a certain sense, actually take that idea of a handler class like that and just kind of boil it down to the bare essentials. Naturally, that doesn't apply to every kind of problem, but it's kind of an interesting facet of that. And as just another follow-up to that, it turns out that coroutines execute pretty quickly as well. This is a little benchmark that I did where I basically sent 1 million lines of text into an object like I had defined versus sending it into a coroutine. And you can sort of see there's a fairly substantial kind of performance difference on that. It's like the coroutine version, is 0.6 seconds, and the object one is 0.9 seconds. Where the difference is coming from is that if you're in a coroutine, you don't have any of these self lookups like you would have on an object. I mean, basically you're omitting like a whole, get attribute operation. You're saving a little bit of time there. So any questions about that stuff before we get into this next section here? All right, moving right along. So what I want to do in section 3 is actually kind of show a different application of coroutines. And one of the things that's kind of interesting about coroutines is that they actually fit in really nicely into certain kinds of applications involving event streams, like event-driven programming, reactors, things of that nature. And I thought I would look at an example of this, which is the where's my bus problem. One thing for those of you out of town, or maybe even those of you in town, might not know, City of Chicago equips most of its buses with GPS trackers. And it turns out if you know the right website to go to, you can actually get the current location of every bus on the street as a big XML document. So this is, you can use Google to kind of search for that, but this is sort of a sample of what the data looks like. So you can get XML data on city buses. Just as a digression, it's not clear that the city knows what they're publishing. Apparently the operator, here's the employee ID of the person driving the bus. So you can get that too. So what I wanted to do is actually look at XML parsing with coroutines, partly because it's actually an application that I think a lot of people have already done. I'm guessing that a lot of people here have parsed XML. I also have this secret desire to introduce yet another XML parsing technique to the world. Like it really absolutely needs that. I'm kidding partly about that. But what I want to do is actually look at XML parsing with coroutines, because it's kind of an interesting angle on how they can be used. So what I'm going to do to set that up is actually start with this SAX parsing interface to XML. Just out of curiosity, how many people have used that, or at least seen it? What's your take on SAX parsing? I mean, is it kind of, it's kind of low level. If you've never seen SAX, basically what you do is you have to define a handler object that has a whole bunch of sort of callback methods in it. So this is sort of a bare bones example of it, where you define a class that, for start element, end element, and characters, and then you essentially hook it up to some parser, and then it just fires off methods in the class. So I do have an example of that on the machine here, sort of a SAX somewhere here. No, that's the coroutine version of it. Well, I'll open it up. Basic SAX. That's probably it. So if you okay, so there's basic SAX. So this is sort of the most minimal sort of SAX example, and if you run that, okay, you just get basically just a bunch of low-level events. It's not actually this slow. That's just idle, not really running very fast there. So one of the things that you can do with this SAX thing, and this is kind of an experiment on my part, is well, first of all, if you use SAX, it's kind of awkward. I mean, basically, this whole event-driven nature of it is pretty weird to work with. I've actually never written any SAX code that I particularly liked. It's not my favorite module to work with. But I had this idea that, essentially the way that SAX works is that it's firing off events. It's basically saying, here's like start of an element, here's a bunch of characters, here's a end of an element, and so forth. One of the things that you could do is maybe just create a SAX handler where you just take in a target, which is actually going to be a coroutine, and then what we're going to do is actually just take all of these events and just fire them off into some coroutine instead. So this is basically a version of this SAX thing where in the start element, characters, and end element, I'm essentially just going to send a tuple where the tuple essentially has an event type and the value has some information about what got parsed. So you have 3 events, start, end, and text, and then the value could either be, the tag name in a dictionary and so forth. So just as an example of what that looks like, okay, so here's sort of, example of an event handler. It's just taking a target, just firing stuff off. Here's a very basic printing function that all it does is just receive events and print them out. So if I were to run this, you essentially are just getting a big stream of events. They show up as tuples, but you essentially have start events, text events, end events, and so forth. And so I've kind of set up this little coroutine thing. And then what I'm sort of thinking about is like, well, what could I do with that? Just as a digression, by the way, I've set this up to kind of mimic what you can do with the element tree module in Python. I don't know if you have not used that module. It has a iterative parsing mode that kind of works in the same way as that. It's not entirely the same, but it's very similar. So I had this idea. Okay, so it's like we're basically have taken SAX and we've just taken all the events and we're just firing them off onto some coroutine. What would it look like to actually use something like that? So as an example, I decided I would write a coroutine that would basically take all of the bus elements and just turn them into dictionaries. So I like dictionaries a whole lot more than I like XML. So here's sort of an example of a coroutine that does this. Now I'm gonna kind of take you through the different pieces of what's happening here. But what this coroutine is doing is essentially up at the top here, it's just receiving an event and a value. So remember that an event is just it's either start, end, or text. Value is sort of what value got passed along. And what this code is doing is it's essentially receiving events looking for the start of a bus element. Okay, so it's basically just sitting there waiting until a bus shows up. And then once it gets a bus, it actually kind of goes into a different state of execution where it's going to start collecting all of the inner elements. This is actually an example of what somebody asked about earlier. Could you have yield statements in 2 different spots in a coroutine? This is sort of an example of that. I mean, basically it's looking for a bus. If it finds one, it drops into a whole different set of code that's sort of collecting data into a dictionary. And if you kind of sort of look at what's happening here, this code is essentially implementing a kind of state machine. It might look a little bit funny in how it is set up, but basically there's a state where you're looking for buses. If you get a bus, you go into another state where you're sort of collecting attributes. And then when you get to the end of a bus, you go back to the original state. So it turns out that in that code, sort of the state A is kind of up here. This is sort of the looking for buses. And this business down here, this is essentially state B, where you're collecting bus information. So that might be kind of a complicated example, but essentially we're taking events, kind of processing them, and so forth. One thing in the code that I'll sort of point out as well is at the end here, this target.send, what I'm doing is when I get a completely formed bus dictionary, I basically fire it off at some other target. So if you kind of wrap your brain around this, what's happening is it's essentially taking that XML stream, grabbing buses, turning them into dictionaries, and then it's just like slamming them out to another target. Let me see if I have an example of that. Code 6. I might have it in the buses example. Actually, I have a couple of more pieces that I'll show you, and then we'll run that. Any questions about what's happening with that? it might make your brain hurt a little bit the first time you see that, but it's, again, you're sort of receiving values and processing them. It turns out that if you kind of expand it a little bit, what I've got here is actually some different processing stages that you can implement. This is essentially a filter where it receives a dictionary of bus data and then just looks for a match on one of the fields and then sends it along. So you can do things like filter on like a specific route. You can then do a filter in like a certain direction or something of that nature. This is another coroutine that basically receives bus dictionaries and just prints them out as a big table. And then what you can do is just kind of hook a whole bunch of stuff together. So I'll sort of show you this code in some detail here. But what you can do with it is essentially you can take that sort of that XML SAX thing. You can stack together a whole bunch of these processing stages. So this is basically creating dictionaries. Here's this filter, here's a printer, and then what you're doing is setting up a bunch of plumbing kind of at the end. So again, it's getting to look very Lisp-like in the number of parentheses there at the end, but what this is doing is it's saying, okay, parse this XML file, and then feed this stuff into a whole bunch of processing stages. So it's going buses to dictionaries, filter out Route 22, filter out northbound, and then print it out. And if you were to run that, on the XML file that's in the directory, you basically get something like that. So it prints out sort of a table sort of showing you all the positions of the northbound number 22 bus. And if you're from Chicago, that's the Clark Street bus. I don't know whether it's the slowest object in the universe, but it sort of competes with the Broadway bus for that title, I think. So, question up front.
When you implement using coroutines, this state machine, this particular state machine is rather trivial. It has only 2 states. If you were to go try and implement something with many states, you're going to end up with a really huge chunk of code because you can't really split a coroutine into subfunctions easily. Is that correct?
Okay, so the question is if the state machine that you were implementing started to get very huge, the coroutine might get completely unmanageable to do that. I would agree on that. One thing that you might do if you had like a really complicated state machine, and this is it's kind of interesting. Basically, what you could do is create like an object that implemented the state machine, and just give it the send and close interface. One cool thing that's about coroutines is they actually have this really simple programming interface of sending data and closing them. Technically, a target wouldn't even have to be a coroutine. It could just be an object that mimicked that same programming interface. So if you did a really complicated state machine, there might be other alternative implementations that you could essentially plug in its place and do that. Unfortunately, I guess we could propose Python have a switch statement, but then I'm already on thin ice with the expression in the while loop there.
If the knight suddenly appears to lop your head off, you will be avenged.
Okay, I would be avenged if the knight appeared. Okay. All right, so that's kind of an example of that, and I think this is kind of interesting because I've actually never quite seen XML parsing done exactly like that. I mean, I suppose other people have maybe played around with it and tried it. I will admit I didn't do like a huge web search to see whether people had played around with that. But it's kind of an interesting sort of take on the whole thing. One thing that's also interesting about this, and this is also why I've picked this example, a really interesting thing about coroutines is that you can push that initial data source as low level as you want to make it. Keep in mind that with a coroutine, the whole thing is basically driven by the send operation. And one of the things that's kind of interesting about that is you can basically move that send operation to lower levels of your program. This is an example that basically uses the XPath library module in XML. If you've ever looked at XPath, it's like way more low level than SAX. I mean, basically there's no good reason to use the XPath module for all practical purposes. But what I did in this is essentially, I kind of cooked up an expat interface where I just was using the same send operation to send events. And so I sort of have an example of what that looks like here. So there's co-expat. Okay, so that the initial source here is really grungy. I'm not going to spend any time going through the details of all the lambdas and grunginess of that. But what's the really cool part about it is that I can essentially take this new source that I cooked up, this expat thing, and then just take like that processing pipe that I cooked up earlier, like all the buses to dicks and filters and so forth. I can essentially just take the whole processing pipe and just drop it onto this expat parser, and it essentially works without any modification. So it's kind of cool that you can essentially swap out the initial data source with something else, and you don't have to change the processing stages. And by doing that, I maybe won't run it right now, but I did a little performance test with a large XML file, and it's like my SAX version, took 8.4 seconds, but the one using expat dropped like 4.5 seconds, giving me like an 80% speed up. So I think that's kind of cool in the sense that I got this huge speed up without actually changing any of the processing stages. I mean, they're almost like their own little self-contained components there. Another element of this, which is probably more subtle, is that send, basically calling send on an object in Python, can actually be dropped all the way into C code. That's probably a bit of an advanced topic, but essentially from the C side, you can get a reference to the send method of an object, and then you can just sit there in C and just do like py-eval call object on it. So so one of the things that you could potentially do is take like a data source and just drop it all the way down into C and just fire send events on it. This is something that you can actually not do with generator functions. Unless I've missed something, I actually do not know how to write a generator in C code. I mean, basically, there's a problem with generators is that you have to preserve your like execution state, and there's no facility for doing that in C with writing generator functions. So the coroutines are actually something you can drop into C. If you do that, you even get a bigger speed up. So I kind of, you can find this in the directory. There's an example where, I kind of wrote a C extension directly on top of expat and stripped it way down, and I got like another 55% speed up doing that. And then one little final interlude. There is some code that kind of compares this to the element tree module. First of all, if you have not used element tree, you're really missing out. I don't know whether people have used it or not, but element tree is like extremely fast and useful for parsing XML. This is sort of an example of doing the exact same thing that we just did in the element tree module. It essentially has sort of an iterative parsing mode, and the code looks a little bit different, but one of the things that you'll sort of notice is that the performance of doing this coroutine business is kind of in the same ballpark as using element tree. It wasn't really my intent to get in a performance contest with element tree, but it's kind of interesting that we've kind of taken this totally different angle on XML parsing, and we ended up with something that's has decent runtime performance. So it didn't completely sort of kill our code by doing that. So any questions about some of that stuff? Okay, stunned silence, or hopefully everybody's not completely lost at this point. So that's kind of a sort of a basic taste of some coroutine data processing thing. The real takeaway on it is that if you've done anything with generators, and you've done things like setting up processing pipes or different, processing elements and so forth like that, what you're really getting with coroutines, you just flip the whole thing on its end, and you basically get the ability to do the exact same sorts of things, but you're just sort of pushing data into the pipeline in a slightly different way. And it sort of lends itself to certain kinds of problems. Like this XML thing, it actually works pretty well at, because we sort of took this event-driven SAX parsing thing and sort of used it to feed a big processing pipeline. All right, so let me see how we're doing on time. We're gonna start getting into the head exploding part of the class in a second here. So any other question in the middle of the room there?
Just a general question. Coroutines and recursion, is it possible or is that evil?
It's basically not possible. So you're talking about, like, the question is coroutines and recursion. Like, can you have a coroutine, like, send data back into itself or something like that? Now, it turns out you can't do that. Now, I'll say more about that in a second. Well, one other digression I'll mention about SAX is you need to make sure that you wear the geekiest Python shirt you can at the airport. So I was out at O'Hare this last fall wearing this tremendously geeky shirt that says Python programming the way Guido indented it. I don't know if you've seen. Have anybody seen that shirt? And so this guy, approached me in the airport. He said, "Oh, I like your shirt." We got to talking. It turned out it was the guy who created SAX, like in Java. So we got to talking about it. It was like, so you need to make sure you wear the geekiest shirt possible at the airport there. He was just passing through O'Hare or somewhere else. So where we're going to go from here is, kind of the story so far is that, coroutines have a lot of similarity to what you can do with generators. I mean, basically, you can create really small sort of collections of small, you can create collections of little processing components. You can start hooking them together. You can create these little pipelines. You can do little data flow things. You can hook them into sort of event-driven systems. I hope it's not lost on anyone that there's no library modules involved in this. I've not downloaded some third-party package. I haven't even done an import on any standard library module. I mean, this is just basically a core feature of the Python language that you can play with. But there's actually a lot of things that you can do with this that sort of take it in a much more interesting direction. One of the things that you can think about is that there's a common theme kind of underlying what we've been doing. I mean, basically, with a coroutine, you send data to it. And if you kind of sit back and you say, well, sending data, that sounds familiar to things I've seen before. For instance, you might send data to threads. Okay, if you've done any thread programming, you might have done something with threads and like message queues and things of that nature. Or you might have seen things just like, like producer-consumer problems. It's kind of a classic thread programming thing. If you've done any kind of distributed computing or networking, you might know about, sending data to processes or across the network. And so if you look at this, you're saying, well, there's a lot of like similarity sort of tying all of these ideas together. And one of the things that you could think about doing is using coroutines as kind of like a basic building block of things that are more advanced. So if you're looking at one of these coroutine functions, it's like, well, why couldn't a coroutine run in a thread? I mean, I can't think of any reason why I couldn't run it in a thread. So if you're looking at building a larger system, you might potentially have like a source feeding data into threads in which there's an embedded coroutine. And I'll show you an example of that in a second. Why couldn't a coroutine live in a subprocess? I mean, I could launch a subprocess that had a coroutine, and then I fed data to it over a pipe. And we'll look at an example of that. Why couldn't a coroutine live on a completely different computer across the network, with a socket connection? The fact that coroutines basically have this one interface of sending and closing, I mean, that lends itself to tons of different possible execution modes of that. So So here's sort of one idea of doing this. This is basically one way that you might get a coroutine to actually run in a separate thread of execution. The way that this works, I'll kind of step you through it, is that first of all, I'm going to use a message queue to basically coordinate the sending process. So if you're going to run something in a separate execution thread, the idea is that we're going to basically launch it, and then we're going to hook a queue up to it where we send data to it using that queue. Here's basically the execution thread. So this might look a little bit funny that I've defined this as a nested function, but I'm just trying to keep the amount of code kind of low here. What this is it's basically a thread that just runs in an infinite while loop, pulling items off of that message queue that I got. So here it's basically saying, give me a message. This little bit of code here where it's checking for generator exit, I'll explain in a second. But essentially what's happening is this thing is just pulling off items and then sending them to some target. This target, it turns out, is going to be a coroutine. This statement here, thread, I'm basically just launching the thread. So this thing is basically going off into a completely separate execution thread and then just firing like messages off at a coroutine. And then what I have here is this is more of the producer for that message queue. This is basically code that's using yield to essentially receive values, and then what it's doing is putting them onto that message queue. So part of what's happening here is we're kind of building a bridge where we've got a coroutine that's going to suck in a bunch of values, and then it's just going to pile them onto some separate thread of execution that's going to deal with them. This generator exit business is a little bit tricky, but what I'm doing with this message queue is that if the pipeline shuts down, so somebody calls close on the coroutine, I'm actually just going to drop generator exit onto the message queue, and then if I get it, I'll forward the close operation on in the thread. That's a little bit tricky, but you can play with that. So an example of doing that, one of the things that you could do is I could essentially just set up my same processing handler where I'm just saying, okay, buses to dictionaries, and then I just throw like threaded like in the middle of it, like that. And what you'll get is essentially kind of a program that looks like this. Essentially, you have the main program is kind of feeding part of the pipeline, and then you have this intermediate sort of step that's basically firing messages over to a completely separate execution thread. So there is some code that kind of illustrates that. Let me see if I actually have it up here. Was it there? Code thread. I have too many. Oh, okay, yeah, okay. There's a danger of having too many windows open here. So co-thread. So this is sort of an example of that. And again, what I've done is I just kind of took this XML bus thing and just really just kind of threw threaded just right into the middle of the processing pipeline. I mean, basically this threaded component, again, is just kind of acting as a bridge from the, the original sort of data, processing stages, and it's like firing off into a different thread. As far as I know, that does run, so you can run it, and you're actually seeing some of the threading here. The part of the main program finished before the thread was able to catch up with it, and you saw like you're seeing the interpreter prompt being printed while the other thread is still like trying to catch up. So that's one thing that you could do. So there is this possibility, just like, with a little simple function, all of a sudden you've like thrown this thing off onto a thread. The other thing that you could do is, throw a coroutine off into like a sub-process. This is a little bit more complicated, but what you could do is actually have a coroutine. So this is a function that basically takes a file as input, and what it does is it receives items, and then it just pickle dumps them straight onto a file and flushes them out. So this is essentially a coroutine that's basically just receiving a bunch of data and just pickling it straight across some file interface. And then you could have like a function that's sort of its partner, this receive from, where what it does is it just receives items received over, over a file with pickle, and then sends them off to some target. And so a high-level view of that is you could essentially have a situation where you're basically breaking this processing stage across, either a pipe or a socket. So there is another example of that. This co-pipe is sort of one example where, actually, co-process is the one that I want to look at. So what is happening with this is an example here is I might set up like a sub-process using just the sub-process module. So what I'm doing here is saying, okay, I'm going to run a separate program, this busproc.py. I'm going to hook it up over a pipe. And then what I would do is I would say, parse this XML file, turn it all into dictionaries, and then just send it across the pipe. So in this process, you've sort of got, I'm doing a little bit of parsing and then just sending it off to some other process. And then what I've got in that busproc is I essentially have the rest of the processing. I essentially just say, well, receive from sys.standardin. That's what the file is when you do a pipe. And then I just stack the other processing components on each other. So I can say, okay, filter on field, bus locations. And essentially you've got this thing now running across a pipe of some kind. I'm not sure whether that's actually going to run correctly and idle or not, but if I just go to like a terminal here and say Python, coprocess, like that, you essentially see it run in exactly the same way. So there's sort of, obviously there's some pretty interesting things that are sort of going on here. I would say you probably would not want to do that gratuitously unless you could actually justify the cost of communicating between processes. So you would generally not do that unless there was some way to split the processing up in a reasonable way. But one of the things that's kind of going on here that I think is pretty interesting is that there's almost sort of a separation of the sort of the implementation of a coroutine from the environment in which it's running. I mean, it's almost like a coroutine is just this basic little function that receives data, does something with it, and it's not actually tied to any kind of execution environment. I mean, basically, if you want to run it in a thread, you can just put a wrapper around it. If you want to run it in a co-process, in a sub-process, you just put another wrapper around it. If you want to throw it out on the net, you just have, basically, you could just have like little wrappers around it that essentially set up the environment for it. So I think that's kind of an interesting little element of that. I could think of one caution to be aware of. Maybe going overboard with that, maybe not the best. I mean, it might be a really good way to create a completely unmaintainable application, although it might vastly increase your job security. It also might be a really good way to sort of make your program run really slow as well. I mean, it kind of depends on the problem. But again, it's kind of an interesting. I think it's an interesting aspect of coroutines. It's just this really fundamental, low-level primitive of this function that you send things to, and you're kind of free to do what you want to with it. A couple of other things to be aware of, and then we're going to take a break in a minute here. One thing with coroutines is that send method is not thread safe. This is a little bit subtle, but if you start mixing threads and coroutines together, you can actually crash your program if two different execution threads call send on a coroutine at the same time. So that's one thing to be cautious of. There is a program called co-crash that illustrates that. Let me see if I have that. Where you might have something like that is, let's say you had like the one printer object like this, and then I had two threaded coroutines sending data to that same printer. Basically what I'm going to have is like two threads pounding on one coroutine. If I do that, you can end up with kind of a weird program crash. I'll see what happens here in idle. Okay, you actually got here's sort of what you're seeing in one of the threads. It got this sort of weird exception where it essentially said the generator was already executing. So it's possible that your program will just die if that send is already going. And tied into that, somebody asked whether you can do recursion with coroutines. That actually prevents that as well. I mean, one of the things that you might think about is having like a bunch of sends and then maybe some kind of feedback loop or something where, like a send goes back to something else that was in an earlier stage. That does not work as well. I mean, essentially you'll get a crash doing that. And so that's where we're going to break for now. Give everyone 20 minutes to recover for the next part. What we're going to do when we come back is actually talk about how to write like a multitasking operating system in Python with no threads and no processes. If you've ever used anything like Twisted, this is basically going to twist it around into something completely different. It's actually going to do the same thing as Twisted, but in a totally different angle of a attack. So one question in the middle there.
So this thing that you just mentioned about send and threads seems almost like it's a showstopper for trying to use threads with coroutines.
Yeah, so the question is, is that thing with threads, is that a showstopper or not? I think it kind of depends on the problem. It's also not terribly difficult to fix if you just put it like a wrapper with a lock in it. So, I mean, if you did want to fix that, you could set up like an extra layer around like a coroutine that had, like a mutex lock or a semaphore or something on that. So I think you could solve the problem, but you would have to do it with some kind of locking to get that to work.
Earlier you mentioned the difference between just plain old objects and coroutines, and that there was a little bit of overhead with the self lookup on an object. But it seems like, I mean, what are we getting from coroutines if we're putting them in different threads or processes over, I mean, there's like, what language support are we getting other than, the fact that when it's garbage collected, it calls that extra, or what does it do? It calls that.
Calls close. The question is, I'm trying to understand the question. Sort of like, what are we getting?
Yeah, what are we getting out of coroutines? You said it was nice before comparing it to objects in a small example because there's a little less overhead, but when you create this extra overhead, it seems like it's negligible.
Yeah, you're probably right. So the question is, what are we getting in terms of performance over
just a regular method? It seems like that small bit of performance gain that you got over using a regular object is negligible once you have threads and the overhead of processes.
Okay, so the question is probably that the overhead of threads and processes totally wipes out the performance benefit of coroutine.
Yeah.
I would agree with you. I haven't benchmarked it, but I mean, that little bit of overhead in like a coroutine, once you start introducing blocks and message queues and threads and co-processes and stuff, that's definitely going to be lost in the noise. So what you would essentially be left with is the idea that a coroutine is maybe a very simple software element, in the sense that it's not you don't have to have a class or a base class.
I guess it's
whether that's good or not, I don't know.
Yeah, it's nice that there's language support, but it seems like it's something that could have been done before coroutines were in Python. Just using regular objects.
Definitely. And in fact, all of this stuff that we've done, you don't even need coroutines to do. I mean, it's sort of like if you just wanted to have an object that you send and close, you could definitely just do that. We have one question all the way in the back there.
Is it possible to make a copy of a coroutine? And if so, can it be used to deal with the thread safety problem?
So the question is, can we make a copy of an already executing coroutine?
That's right.
Not that I know of. I don't think so. So, yeah, I'm getting the word from the moderator here that we need to go to break. So
Before all the stuff's gone.
Oh, definitely that we need to break. So, so we'll come back in about 20. One of the things that you'll find if you start looking at some of this coroutine business is that it gets described as a way to do multitasking. And so very common thing that you see is somebody will say, well, we're using coroutines and we can do multitasking with no threads and no sub-processes. And then at that point, your sort of head melts a little bit, wondering, well, how does that work? So I want to get into some details about using coroutines to do sort of multitasking kinds of things. And to kind of set that up, if you start talking about sort of concurrent programming, a very big thing that you hear people talking about is this sort of concept of a task. Now, a task can actually be many different things. I mean, it could be like a thread. It could be maybe a separate process running somewhere. But if you kind of boil it down and you say, well, what is a task specifically? I think there's a couple of like common themes that you see with tasks. One is that a task tends to have independent control flow. So if you're launching like a thread or a process or something, you know that basically runs independently of whatever launched it. I mean, it's like it's its own thing basically. Tasks also have some kind of internal state typically. I mean, they might have their own variables, they might have their own execution stack, some kind of state of some kind. There's often a scheduling component of tasks, like you can have them running concurrently, they can wait for other tasks, they can suspend, they can be resumed. And then there's also an element of communication between tasks. And so if you kind of look at that, I think you could make the claim that a coroutine is actually some kind of task. I mean, it sure looks a lot like a task. Specifically, if you go into a coroutine function, it definitely has its own flow of control. I mean, if you're inside a coroutine, it's executing statements just like any other Python function. So there's definitely control flow inside of a coroutine. If you're inside of a coroutine, all of the local variables that are defined in there are defining some kind of internal state. Okay, so there's definitely some state associated with a coroutine. And all of these variables persist as long as the coroutine is still active. So as long as you haven't shut it down, it's still, all of that stuff is basically alive. There's certainly a communication element of a coroutine. I mean, basically you can send it data, which gets received by that yield expression. So there's definitely some kind of task, kind of communication element of this. And then there's also kind of a scheduling element of it as well. I mean, basically that yield statement suspends the execution of a coroutine. So there is a way for a coroutine to just basically suspend what it's doing. That send function essentially resumes the execution of a coroutine. So if a coroutine is sleeping or not doing anything, if you send it something, it wakes up and starts working on it. Close terminates a coroutine. And so I think if you kind of step back from it, I mean, unless I've missed something, coroutines certainly to me look like some kind of task. Now, it's a little bit weird in that they're not really tied to anything. I mean, it's like a coroutine is not, it's not part of thread programming. It's not a sub-process. So it sort of has this task-like quality to it, but it's not really tied into the usual sorts of things that one thinks about with multitasking. And so a question that actually comes up is, if coroutines are tasks, can you actually do multitasking using nothing but coroutines? Like, forget about threads, forget about processes. Could you actually build like an entire multitasking environment using nothing but coroutines? And it turns out that you can do that, but in order to do it, I have to step back for a second and talk about how an operating system actually works. Basically, if you're going to build like a multitasking program yourself with like no threads and no processes, you actually have to have some notion as to how multitasking actually gets implemented in something else. So this part 6 is actually kind of a crash course in a couple of essential details of this. And the first essential detail is more about just how programs execute on your computer. This is mainly my excuse to put assembly language into a Python talk, which I like to do whenever possible. As I hope that people know, if you write some like C code and you compile it, it turns into a bunch of machine instructions. So this is just some GCC output for the x86 architecture. And if you look at the code that gets produced by the C compiler, it's basically just a bunch of instructions, one after the other, and there's no notion whatsoever of any kind of task switching or concurrent programming. So if you just take a standard program, you just get a bunch of instructions, and there's nothing in there that has anything whatsoever to do with multitasking. And that actually leads itself to kind of a question, which is if the CPU and the programs that you write don't do any multitasking, how is it possible that my laptop computer here can run like hundreds of jobs all at the same time? I mean, sort of what is doing that? And it's a pretty obvious answer. It's basically the operating system is controlling the show and doing all of the multitasking. Now, that actually leads to, okay, so as I hope that people know, the operating system does allow you to do more than one thing on your system. I mean, it's been a while since operating systems did not allow that, but it basically, you know, if you're using Linux or Mac or Windows, I mean, it's basically the operating system is controlling all the switching between jobs and running things concurrently. And in order to do that, it's really essentially rapidly switching between things. I mean, if you have one CPU, it can only run one program at any given time, and if you're going to have like 10 different programs running all at once, the operating system has to rapidly cycle them on the CPU, and sort of at a fast enough speed where you don't notice that they're basically running one at a time. So a question that comes up is sort of how does an operating system do that? Because this is exactly the same thing that I'm proposing to do with coroutines. I'm basically saying, well, I'm going to write this like multitasking coroutine thing. In order to do that, I'm going to have to rapidly switch between coroutines or do some kind of trick to get them to all to run. Looking at what the operating system does is actually a clue to that. So the conundrum that sort of comes up with this is really the following. It's basically, if the CPU on your computer is running your program, it's not running the operating system. I mean, if you have one CPU in your machine, it can only do one thing at a time. And it's either running your program or it's running the operating system. And you get into this question of like, well, how does the operating system, which is not running, take control of your program and do a task switch? I mean, this is basically the topic that you would get into in like a graduate operating systems course of, how does an operating system take control to actually switch between different tasks that are running? And the short answer to that is essentially there's usually two different things that do this. One way that an operating system can get control is to receive an interrupt or a signal. So if you've actually written things like signal handlers, basically there can be some kind of hardware event that comes in, will briefly suspend your program, and the operating system will sort of deal with it. The other technique that an operating system uses to get control is to execute something known as a trap. And a trap is basically an interrupt generated through software. And what happens with both of these is if either of these occur on your machine, the CPU basically immediately suspends what it's doing in your program, goes into the operating system, and runs some code inside of that. And it's actually at that time that the OS decides whether it wants to switch tasks or not. So there is a way for the OS to kind of intervene and do this task switch. Just for the record, I actually used to teach operating systems, and I'll just say if you're at a university or getting ready to take OS, you can just answer interrupts or traps on any quiz for like the first month, and you're guaranteed to get like at least a 75%. So it's those are sort of like the answer to all problems in the first part of OS. So the way that this works, I'm going to show you what it looks like in C, and then there's kind of an interesting twist that this takes. So the way that these traps actually show up in a C program is actually through the system calls that you execute. So if you're in a C program and you say read, okay, this is a low-level Unix command or Windows function where you say, okay, I want to read from a file. The way that gets implemented is in an entirely different way than a normal subroutine. Basically, the way that gets set up is there's sort of an initial sort of setup, and then the CPU executes basically a software interrupt. That's what this int instruction is. And what happens when that gets triggered is your program at that point suspends. I mean, it basically, you're off in the operating system at that point, and the OS takes over. So typically what's going to happen here is you're going to say, okay, I want to read from a file. You're going to hit that int operation, and the OS is going to look at that and say, oh, well, you want to read from a file. I've got to do all sorts of stuff to make that possible. I have to go out to disk. I have to read disk sectors. I've got to do all sorts of decoding. And like eventually, at some point, your program will come back. You don't know when, but essentially you're suspending at that point. So this sort of feature of OS is actually what makes an operating system work typically. What happens, is the system is going to essentially drop your program on the processor, and it's just going to run full out until it hits a trap or some kind of system call. And when that happens, the OS is going to take over, and it might suspend your program for a little while it deals with whatever that system call was. So a very typical program is basically you run to a trap, and then you run to the next trap, and then you run to the next trap, and so forth. So you kind of get this alternating execution mode where it's like run, trap, run, trap, run, trap, and so forth. And it turns out that mechanism is actually how all the task switching tends to be implemented as well. So if you want to know like how Windows and Linux often do task switching, one of the ways that it happens is basically a program will run until it hits a trap. And then usually the scenario here is if you're trying to read from a file, for instance, it might take a while to get the data to come back off of disk. So what the system will do is it will sort of set up the disk access, and then while that's occurring, it will task switch to some other program. So what you tend to see is sort of you'll run until you hit a trap, you'll task switch, and then that thing will hit a trap, and then you'll task switch back. And so what's happening is the system is basically switching between jobs on these sort of system calls that get made. Is everybody okay with that so far? Might be more about operating systems you wanted to know. It turns out if you want to do many different tasks, you actually just take that whole idea and you throw a bunch of queues into the mix. So if you wanted to make something sort of more complicated, the typical internals of an operating system kind of look like this. Basically, you might have one or more CPUs that are just cranking away on jobs. Those are essentially going to run until a trap or a system call occurs. And then what's going to happen is the task will get removed from the CPU by the OS and put onto some kind of wait queue, saying, okay, well, you're waiting for disk I/O. I'll deal with you when it comes back. And then what you have is a ready queue that basically has things that are ready to run. So the whole system is just basically running jobs, throwing them into queues, pulling things off of queues, and so forth. So this is the kind of thing that you would do in a typical OS class, is kind of talk about, well, okay, there's this queuing structure. The system can only run one thing at a time, and things kind of cycle around through there. Now, if you look at that, here's sort of the insight on using coroutines to do multitasking. I'm going to make the claim that the yield statement is actually a trap in Python. I mean, if you think about the behavior of the yield, if you're inside a generator function, you're basically just cranking away on statements, one after the other, and when you hit that yield statement, boom, you stop. I mean, basically, you're suspended at that point, and what's interesting about it is you suspend, but you have no idea where the control goes after that. I mean, basically, you hit a yield, Coroutine generator has no idea what's happening. And basically what happens is the control gets passed back to whoever started the generator function to begin with. And you don't really know what that is. Could be any bit of code. But it turns out that if you treat the yield as basically basically as this trap instruction, you can actually build sort of a multitasking operating system in Python. And so what we're going to do in this next section is actually build a little multitasking OS entirely in Python using coroutines. It has the potential to sort of blow minds a little bit, so I'll just forewarn everyone in advance. And we have a question in the back before we go on. Yeah.
Back on slide number 91, you wrote send doesn't suspend coroutine execution.
Right.
So it works differently than a generator then, or it doesn't?
So the question is send does not suspend a coroutine. Send is a little bit weird. It's almost like making a subroutine call. Like you basically, what happens with send is you do a send, it essentially goes into some other bit of code, and then you end up kind of building up like a call stack. And then when the send finishes, it basically unwinds the call stack. So it's a little bit weird. It's like basically when you hit a send, the coroutine is essentially doing a sort of a subroutine, and control will come back to it when the send's complete, essentially. I don't know that that really answers your question accurately, but really the only way that a coroutine suspends in Python is through the yield. Another question in the back.
Going on now, 109 now, where we are. You're saying that the control is passed back to whoever made the generator function run, or
right.
Whoever sent the send.
So whoever, so this here, when you hit a yield, you're essentially going to go back to whoever made the coroutine execute. So they will actually pass control back to whoever called the send function, actually.
Send what the original generator.
I didn't quite hear that.
So someone started the generator.
Right.
Then somebody else sent a send in. It goes back to whoever sent the send, right?
It goes back to whoever did the send, yeah.
It's a generator, it's a next, right?
For generators, it's a next.
Yeah.
So in the case of a generator function, it would be whoever called next. In the case of coroutines, it's whoever calls send. There's a paper that talks about this. I'd have to double check the terminology, but I think what you're seeing here is this is an example of what's known as an asymmetric coroutine. Basically, when you send something into a coroutine, control is going to come back to the point of the send operation when it's done. There's another style of coroutines where the sends end up being completely sort of asynchronous, and where, I mean, basically you can do all sorts of sends, and then the control flow sort of works in a totally different way. I don't really want to quite get into that landmine, but you might, if you're interested in that, you can ask me about it later. So what we're going to do is build an OS. So this is a little bit scary, but it's kind of a fun little project. So what we're going to do is build a little multitasking operating system using nothing but Python, no threads, no sub-processes, no event-driven programming. So we're not going to do, if you've done twisted kinds of stuff, we're not going to do that. We're essentially going to do the whole thing using generators and coroutines. And so what I'm going to, the motivation for doing this is really this. If you look out in the kind of the Python world, there's a lot of interest in threading alternatives. So usually it's associated with some kind of flame war associated to the global interpreter lock, which I really don't have a huge opinion about, to be honest. But there's a lot of talk about, well, threads suck. Maybe we can, there's some alternative to that. It's also tied up with things like non-blocking and asynchronous I/O is sort of an element of this. You hear about people trying to run, servers with like thousands of open, keep alive connections. I would say twisted kind of falls into this whole space in a big way. But coroutines are actually kind of a whole different twist on the same problem. So we're going to see how this works. So the first thing that we're going to do, and try to take it at a reasonable pace, is I'm going to define an object which represents a task. And I have this in a file, pyos1. And what this object is it's basically a wrapper around a coroutine. So let me look at that. Pull that up. The reason that I put a wrapper around this will become evident in a little bit, but essentially what this task is it has a target. That's basically going to be a coroutine. And the task, I'm actually going to use an integer task ID, the purpose of which we'll see in a little bit. So tasks basically have like a TID. It's analogous to like a process ID on an OS. And a task basically only knows one operation, which is run. That's the only thing that you can do on a task. You can basically say run. What that's going to do, the way we have this set up, is that running a task basically involves sending it something to get it to run. Okay, so send is basically how you get a coroutine to execute. And one of the things that I'll talk about in a second, it is possible to, with coroutines, you can send in a value when you run it. This task basically has an attribute which holds the value that's going to be sent in when the coroutine executes. So what this object is basically just kind of a wrapper around some coroutine. If you hit run on it, it's just going to basically send in some value, and this will run the task until it hits a yield statement. So here's sort of an example of how you might use something like that. Basically, what I've got here is a function foo, where I print part 1, and then I yield, and then I print part 2, and then I yield, and then it's done. So the way that this is going to work is if I create a task on this thing, and I say, okay, T1 is a task, if I say T1.run, it's essentially going to advance that coroutine one yield statement. So if I run that, let's look at the output of that. What you're sort of seeing in the control flow here is essentially this print statement starts up first. That's the running foo. I say T1 run, and it basically launches into this coroutine, and you see part 1 yield. Okay, so it basically goes bam to the first yield statement. At that point, we're basically back here, after that run function. So I print out resuming foo. Okay, so there's that message. And then when I hit run again, I basically see the part 2 executing. So what you're seeing here is kind of a back and forth between that coroutine and this sort of code here. It's basically say create a task, run it. When it hits a yield, it comes back. If I want to run it again, I just hit run on it repeatedly. What I'm really doing here is mimicking that run trap business. Question in the back.
How is this different from like the cooperative multitasking and stackless or something? It seems similar.
Can you repeat the question?
It seems very similar to stackless cooperative multitasking. Is that?
It's definitely similar to. So the question is it similar to stackless? It's very similar to stackless. Stackless predates this by many years. So I'll say a little bit about stackless Python later on, but stackless, if anything, is maybe a motivator for a lot of these features. For many, if you're aware of stackless Python, I think they've been trying to get features like this into Python for some time, but for whatever reason, have met like resistance on it. So let me come back to stackless a little bit later. If you have used stackless Python, by the way, you're going to start seeing a lot of similarities to what we're doing here. So let me come back to that a little bit later. Is that okay? Okay. But sort of getting back to what's happening here, again, what this is doing is it's basically mimicking this. Essentially, the run runs until you hit the yield, and then when you run again, you go to the next yield, and so forth. So it looks a little bit weird, but that's what we're doing with that task object. Another question, yeah.
So I noticed in the code you said it was a generator / coroutine. So you could wrap either a generator or a coroutine in your run in a task.
Sure.
Okay. So
now we are going to talk about this yield statement a little bit I mean, if you look at that, that just looks like a generator function. It's just a bare yield. I'm not actually really processing any data sent in or received, so or sent back. So okay, so let's move on a little bit. Okay, so this is kind of interesting. It's like this function that you can run, and then it comes back, and so forth. It turns out that if you understand that you can basically advance a coroutine to the next yield, that is actually what you use to implement a task scheduler. So this is a fair bit of code here, but what we've got is if you want to build like a little multitasker, what you're first going to need is a queue of tasks. So that's actually the most critical starting point. So you need a queue. This is basically going to be a holding area for every task that is ready to run. But since I can only do one thing at a time, I sort of need to put tasks someplace. So this is basically where things that can run will go, but it's not actually a set of things that are running this second. I have a method on this scheduler which basically introduces a new task into the scheduler. What this is doing is this target is actually a coroutine that I'm passing in, and I'm wrapping it with one of those task objects. So this is more of just kind of a code cleanup thing where I'm saying, well, add a new coroutine into the scheduler. What it does is it basically wraps it up with a task object and then puts it onto this queue. One thing that I do keep inside the scheduler is I'm going to have a dictionary that maps task IDs to tasks. I'll say more about why I have that a little bit later, but essentially every single task has an integer identifier, and I'm going to use that for certain things later on. This method basically puts a task onto a ready queue. So all it does is just put something on the queue there. And then as far as how a scheduler works, it's basically just a big loop. What this thing is doing is it's essentially looping while there are actually any tasks. So this task map is basically a dictionary of things that are sort of there. And what I'm going to do is just pull things off that ready queue. I mean, it's basically give me a task, run it, and then when that run returns, I'm just going to put it back onto the queue. So if you kind of play around with this, let's look at a bit of code. You're essentially taking what we just did and kind of packaging it up into a little bit more complicated setup. Essentially, what you can do with this scheduler is I can take two different coroutine functions like foo and bar, do a print statement and a yield, and then what I can do is I can say, okay, create a scheduler, add foo as a new task, add bar as a new task, and then just do a loop on it. So basically do a main loop. What that's going to do is it's essentially going to alternate between those two tasks, sort of cycling them around on a queue. So you may not believe it, but if I run this, okay, there you get output that looks like that. Basically runs forever, saying I'm foo, I'm bar, I'm foo, I'm bar, I'm foo. And basically what's driving that is this main loop thing is just saying, give me a task, I'm going to run it to the next yield statement, and then when it's done, I'm just going to put it back onto the queue to come around the next time. Okay, so that's a fair amount of code to just sort of throw in, right that second, but hopefully that makes some sense as to how that's working. Any questions on that? Yes?
Do you have result in there just to show the fact that you're ignoring it?
I have result in there because I'm going to use it in a second. So the question is why am I saving the result of the task run there? We're going to use that for something shortly. Okay, so simple little scheduler. There is a problem with it. I've kind of glossed over one little nasty bit. If I were to change one of the tasks so that it maybe like terminated after some number of iterations. So if I change the task to just count to 10 and then fall off, if I were to sort of run that version, basically the whole scheduler dies because when you fall off the end of a coroutine, you get that stop iteration exception. So one little tweak that you want to make to this is you probably want to add some kind of catch for task termination. It's not actually that hard to do, but what you can do is essentially do a try except on that stop iteration. And then what you can do is I actually have an exit method of the scheduler which removes that task from sort of the map of active tasks. So if you look at sort of that version, it's basically the same as the last one, except that, you know, again, there's this kind of this extra termination method, essentially removing the task ID from that dictionary. And then again, you kind of have some try and accept things here. So if you were to sort of run that version, so here's a version where both of these tasks actually terminate. And you were to run that, what you'll see is kind of, you know, this sort of thing. I mean, they basically alternate back and forth. When one of the tasks terminated, I actually had a print statement just to kind of, that's more of just a debugging diagnostic saying, hey, it terminated. And it essentially runs until there's no more tasks. So it's kind of a slight sort of tweak on the last example. All right, is everyone with me so far? Key point, just to emphasize what's happening here, is that the yield is a kind of sort of like a system trap. The scheduler is basically just running things until they hit the yield, and then it's rapidly cycling between tasks. It's kind of doing a little round robin thing where it's like you get to run until you yield, and then the next task runs until it yields, next task runs until it yields. And we just do that sort of forever until there's no more tasks to work with. All right. Now, where this starts to get, now this is where it starts to get kind of interesting. One of the things that I mentioned in the OS section is that traps are basically how an operating system does things on behalf of a program. Like if you're in a C program and you're doing system calls like read and write and sleep and so forth like that, when you execute those, there's actually some information that goes back to the operating system that says, hey, I want to do a read call. So one of the things that you can look at is this, in our little scheduler here, is that basically that scheduler that I wrote is the operating system. I mean, it's basically running tasks, putting them on the different, you know, basically saying you run, now you run, and so forth. So that scheduler is essentially the OS. And the yield statement is the trap operation. One of the questions that you could ask is, well, how could a task request a service from the scheduler? Like, how could a task ask the scheduler, put me to sleep, or something like that? One of the ways that you could do that is actually to use the yield statement with a value coming back on it. So this is going to look a little bit wild, but one of the things that you can do is I created a special object called a system call object that has one method on it called handle. And what I've done is I've modified the scheduler so that it will run the task, and then it will look at the result that came back and see whether it's whether it's like a system call object. We're going to see how this works in a second. So I sort of have this base class for sort of a so-called system call, and here I'm going to see whether one of those came back. One of the tricks that you can do in the scheduler is you can essentially use this where you say, okay, if a task returns one of these system call objects back to me, I'm actually just going to do some sort of setup and just run it on behalf of the task. This looks a little bit weird, but basically the scheduler is going to get one of these sort of system requests back, and then we'll just execute it on its own, kind of behind the scenes. And so if you kind of play around with this, what you can start doing is implementing really simple sort of scheduler system calls. This is an example of one that returns the task ID back to the task. So let me pull that up and just kind of step through this, because this is where the control flow of this gets a little bit wild looking. So the idea of how this is going to work is, okay, so I might define an object that represents a kind of system call. GetTid basically gets the task ID. In order to use that, what I can do in one of my coroutines is do this little trick. Now this looks a little odd, but what I'm doing is I'm saying yield GetTid in the middle of the coroutine. What this is going to do is this GetTid thing is basically going to create like a system call object, and it's going to pass it back as the result of this task run operation. Basically, when you do task run, that's going to run until you hit the yield, and then what's going to happen is that weird system call object is going to come back. And what I'm using there is a little trick where I'm going to say, well, if it's a system call that came back, me as the scheduler I'm just going to go off and run that at this point. So if that's what came back, I'm going to do a little bit of setup. This business here is basically saying what task requested this service, and there's a link back to the scheduler. And then I just fire the system call handle method. I just say, okay, go run whatever that system call is. And what you do in here is you essentially do whatever the processing is behind the scenes of that. What I'm doing here is I'm essentially setting up a value to send back into the coroutine when this thing gets scheduled again. So this is almost setting up like a return value. And then what I'm doing is just dropping this onto the ready queue. So the control flow of this is kind of wild, but it's like basically what happens is this yield comes back into the scheduler here. It basically runs some kind of behind the scenes system action. That system action basically puts the task back onto the ready queue. And the result of that essentially comes back from the yield statement the next time it runs. There will be a quiz later on what is happening here. But one way to think about it is that this yield business, it's kind of like requesting a subroutine run inside of the scheduler, sort of behind the scenes. So if you run that, you now get output where there's sort of this thread ID number or this task ID number comes back as a value. I would say that this facet of this task schedule is probably the most mind-bending thing to get over initially, and I think I have a comment on that. One of the things that's going on here is something that comes straight out of operating systems. A really big part of designing an OS is actually maintaining separation between things. So if I'm writing like the Linux kernel, I don't allow application programs to link directly into the Linux kernel. Okay, I mean it's like an essential part of like keeping your system stable is not allowing tasks to basically muck around with stuff. And if you were designing an OS, I mean, basically, tasks don't see the OS, and tasks are not supposed to see other tasks. Essentially, the only interface to the outside world that like a normal program has on your machine is the trap instruction. And what we're doing in this part of the code is actually trying to emulate that. I mean, basically, when we say yield GetTid, if you look at that, there's no reference to the scheduler there. I mean, there is a reference to this GetTid object, but we're not linking to the scheduler. We're not referencing other tasks. We're not calling like some subroutine method on some object somewhere. I mean, basically, we have this one thing that we can do, which is to yield some object, and that's it. And it may take a little time to kind of wrap your brain around that, but what I'm really trying to do is emulate the kind of protection levels that a typical operating system has. Is everybody kind of with me on that, or yes?
Why does the getTid handle method, it's like it expects that the scheduler added some attributes to the result, or added attributes to it?
Right.
Is that normal, or?
I don't know whether it's normal, it's just what I came up with. So I probably could have defined handle to take, actually it probably would have been better to do that. Just have it pass in what the task was and what the scheduler was. I mean, a critical thing about system calls is they're always done on behalf of some task. So you actually have to know which task you're actually working with. So what this getTid thing is doing is basically trying to get the task ID, and then it saves it in this magic, this send eval attribute here. Keep in mind that send eval is actually what got passed into the send operation when you ran the task. So we're kind of doing a weird return value there. All right, so we're ramping up the curve there. For those of you at the beginning of the class saw the big curve out, kind of went steep towards the end there. Once you start messing around with system calls, there's all sorts of things that kind of can come into the picture. One of the things that you might want to do is things like, let's add some operations to create tasks, kill tasks, and wait for tasks. This is a common thing that you often see with threads or processes. So one of the things that you can do is actually start going off and implementing things like this system call. This is a new task that basically takes a target, and the handling of this is basically to add it to the scheduler and then schedule it. So the way that this is sort of set up is, let me go to Pi OS 5 here. I essentially can add, sort of this new task operation. And what I can start doing is writing tasks which end up doing things almost like a process fork. So what I can do is I can say things, okay, launch a child task, which happens to be this foo. And then you can start getting into little task management sorts of things. Another thing that you can do is I added a kill task system call. So what does kill task do? Basically what it does is you give it a task ID, and it essentially just calls close on it. So that basically sort of nukes a coroutine by closing it. And if you sort of add that kind of stuff into your scheduler, you can start doing things like this. So this main program is basically saying, launch a new task foo. I'm going to yield 5 times, and then I'm going to kill it, and then do a task done. So this is almost like some kind of thing that you would do with Unix process forking or something. So you run that, and essentially, prints out I'm foo, and then all of a sudden task 2 just gets terminated abruptly, and then main basically exit. So there's certain things that you can do as far as you can start launching tasks, you can start killing tasks, and again, the way that this is set up is that the tasks themselves basically just do this yield, saying, well, I want a new task. And keep in mind that operation, there's no reference to the scheduler or anything about that. It's just give me a new task. And we've essentially got to have things sort of very sort of decoupled there, if you will. The actual creation of the task runs back behind the scenes in the scheduler somewhere. So questions about that? Everyone okay so far? Yeah, I've seen a few people with the head exploding thing. Hopefully you don't mind. It's good to have a little head explosion from time to time. So here's kind of an example of some basic task control. and some output of that. It turns out that you can wait for tasks as well. So one of the things that you could do is you could implement an operation to wait for some child task to exit. This is actually where things start to get a little bit more tricky in a task scheduler. So let's say this function main here says launch foo as a child, and then it wants to wait for it to exit. In order for that to work, this main basically has to remove itself from execution until some future point in time. I mean, basically, if you're waiting for something, you can't just like proceed with running until what you're waiting for has actually occurred. And so to deal with things like that, you start getting into other kinds of scheduler changes. And the way that you do it is if you're going to wait, like if a task is going to wait for something, you actually have to have some kind of waiting area. So what happens here is there's essentially a dictionary that's just essentially a collection of tasks that are waiting for some other task to exit. It's actually just a dictionary that maps sort of like task IDs to sort of task object. And what you can do with that is you essentially are going to make modifications where if a task exits, it's going to go look into that waiting area saying, was anybody waiting for me to terminate? So in the exit operation, you're essentially going to say, well, okay, did anybody call wait? I'm going to go check that exit waiting dictionary just to see if anything's hanging around. And what you do is essentially take everything that's waiting and then just drop them back onto the ready queue. I mean, essentially, if you're exiting and somebody was waiting, the way that you would get that waiting thing to run is to drop it back onto the queue. And then I have another method, which is kind of the wait operation on that. If you're waiting for a task, essentially what you're going to do is a couple of things. And one of the things that you're going to do is check to see whether the thing you're waiting for has already exited. So if it doesn't exist, you're just going to return immediately saying, well, I didn't see it, so it's probably dead already. Otherwise, you're just going to end up putting yourself into that waiting area. So this definitely looks a little bit more tricky, but what this wait task is going to do is it's essentially going to kind of play around with that scheduling thing. It's basically going to say, well, if that child is still running, I'm going to go off into the waiting area to hang out for a bit. If it's not running, like it's terminated, then I'm just going to return immediately. So it's a little bit tricky to wrap your brain around. But if you sort of run that, you can essentially do things like task sort of waiting and launching operations. So this PyOS 6, what's happening with that is essentially you have this ability to do really simple sort of task management. I mean, basically the main program is saying, okay, launch a new task. I'm going to print out waiting for it. And then I'm just going to hang out, and what will happen is this main will just kind of wait until this foo finishes whatever it's doing. So you may not believe it, sort of looking at it right this second, but essentially you've implemented a sort of a kind of basic sort of task management there. So like fork, wait, join, kill, and things of that nature. Wasn't a lot of code to implement that, but it's a little bit sneaky in how it works. I would say that the main feature of it is that if you're going to wait for something, you have to essentially remove yourself from the run queue and go hang out in your own area for a while. So questions about that? Head explosion at let me see how I'm doing at time. Okay, 4:04. Okay, we're doing okay. At 4 o'clock in the afternoon, talking about that is probably a good thing. Okay. Well, if you have basic task management, okay, well, actually, let me talk about a design element of this. One thing that I'm doing here, again, is very much an OS kind of design that I'm taking here. One of the things that I'm really thinking about is like a data encapsulation and safety element of this. And one of the purposes of that task ID was basically to make it that so that other tasks never directly refer to any other tasks in the system. If you kind of wrap your brain around that, we're essentially trying to keep things really separated from each other. I mean, basically tasks do not talk to the basically tasks do not manipulate the scheduler object. Tasks do not manipulate other tasks. So there's no direct linking where, like, if you create like a child, you never get any reference to the coroutine that implements that. All you do is you get the task ID, which is an integer. If I want to do something with it, I have to go through the scheduler. And again, that's very much a kind of an OS concept where, in order to keep your brain from completely exploding or your system from dying, you really try to keep things isolated. So as an interlude here, it's pretty amazing what you've got here. I mean, it's basically you've got running multiple tasks. You can launch new tasks. You can do some basic task management like killing, waiting, and so forth. Basically, you're ready to write a web framework at this point. Okay, well, I'm not going to do that, but I think I'll start with something a little bit more simple, which is just an echo server. So what somebody might do with this is actually just try to implement like a standard sort of thing that you would normally do with threads or forks. So hopefully people have seen like basic network programming before, but what I'm going to do here is I'm just going to implement a server coroutine here that just opens up some socket, waits for a connection on it. So that's what this business at the bottom here. So it's just a server loop where it's like, give me a connection. And then what I'm going to do is just launch some task to handle the client. This is like standard like server programming kind of 101. It's like get a connection, go launch some client thread or something to deal with it, and then I'm going to go back listening for more connections. And then up here, I've got some function to basically, handle the client, and then, okay, as I'm going to read some data, I'll send some stuff, and when I'm done, I'll yield to, whoever. It turns out if you implement that, doesn't really quite work in the way that you would want. So if you fire up, I think I have a program, echo bad here. This is essentially kind of a flawed version of this. So I've kind of got this server that is supposed to run concurrently. Okay, so there's the server. Since this whole thing is supposed to be able to do multitasking, I actually wrote like a little alive task just to see whether the thing is still operating. So this task is just going to sit there printing, I'm alive, I'm alive, I'm alive, I'm alive. If you run this thing, it just does not work at all. Like if you run it, it just ends up like freezing. And then like nothing happens. You're not seeing any alive messages. I think even if you tried to sort of telnet into it, I'm not even sure it actually works. Like if you were to telnet into localhost 45,000 to connect. Well, okay, I did get a connection message there, but well, I don't know. Let's see what happens. Okay, well, it is working, but it's like my alive message is not working. If I were to go over to another window and try to telnet, I mean, in theory, this thing is supposed to be concurrent. It's like that one doesn't respond. I mean, basically, the whole thing is just kind of screwed up at this point. And the reason it's screwed up is that these operations, like accept, are basically blocking. So hopefully you know that if you do things like accept or read or something just in a standard Python program, it puts your entire process asleep until some data shows up. And this is a pretty problematic for our little multitasker because we're not using any threads or processes. So if somebody puts the entire Python process to sleep, everything goes to sleep. I mean, basically every task just shuts down. And it does not work in the way that we want. So To deal with this, and this is where this whole technique kind of meets up with something like Twisted, actually. One of the things that you can do is kind of this non-blocking I/O scheme. You might know about this library module in Python, the select module, where what you can do is essentially you can basically pass this select function a list of different socket connections, and then you can do a polling operation. You can basically say, give me all the sockets that actually have data available for reading, give me all the sockets that are able to write, and then what you can do is kind of process that after the fact. If you look at something like, like Twisted, or if you're really hardcore, the async core module. Does anybody have the unfortunate pleasure of ever playing with that in the standard library? Basically what happens in those tools is they'll do like a select like this, and then they start firing basically event callbacks into the system saying, well, this socket can read data, and then you get this like cascading sequence of like event-driven stuff. It turns out that we can use this same trick to deal with blocking I/O in our OS, but it's actually going to take a completely different flavor than that event-driven thing or approach that you see in sort of these asynchronous frameworks. So I'm going to kind of show you what this looks like. Basically, to do it, you have to do the same trick that I did with that wait operation just a second ago. If you're going to wait for a socket, or wait for a connection, or wait for data, you have to go someplace to wait. I mean, essentially your task has to leave the queue of all the running tasks, and it has to go out and hang out somewhere. So what I've got here are essentially two different holding areas. I have a holding area for tasks that are waiting to read, and I have a holding area for tasks that are waiting to write. So these are essentially going to just be dictionaries that are kind of mapping file descriptors to tasks that are sort of associated with them. And so I have sort of these waiting areas. I have a couple of utility methods that actually just put tasks into those dictionaries. So this wait for read operation basically takes a task and a file descriptor, and it just records it saying, okay, this file descriptor is waiting to read, and this task is interested in the result of that. So we're really just kind of building up some maps where we're saying, we're basically building up a bunch of file descriptors and tasks saying, well, these are waiting for reading, these are waiting for writing. To deal with the actual reading and writing, I can actually write like a little polling method. I'll show how this plugs in a second, but what this does is it basically looks to see, this if statement is basically saying, look, is anybody waiting to read or write right now? So it's going to look at those two holding areas and say, is anybody hanging out waiting for I/O? If so, I'm going to do this little select operation. Again, keep in mind, this is the whole key to those things like async core and Twisted and stuff like that. So I'm doing a poll there where I'm saying, look, just tell me if any data is available on any of these file descriptors. And what I'm going to do, and this is the kind of neat trick, is if there's any of these sockets that actually have data or are ready to go, instead of doing some kind of event callback, I'm just going to drop the task back onto the ready queue. So I don't actually do any kind of event-driven thing here. What I do is I just say, oh, if there's something ready for you to read, I'm just going to take your task and just drop you back on the queue, because I know that if you try to read, it's going to work at this point. So this I/O polling thing is basically, it's looking at the socket saying, if you're ready to go, I'm taking you out of the holding area. I'm going to put you back onto the queue. As far as when to do this polling, the only other thing you have to worry about is like actually doing this check for I/O. So one of the things that you might do is in this sort of main loop of the scheduler, you might have to instrument like an extra operation in there saying, okay, well, I need to check whether there's I/O coming in, because if there is, I need to take things out of that holding area and put them back onto the queue. that is one approach to that. I actually took a different approach in the implementation. It turns out you can put the I/O polling into its own task. It's kind of a weird, sneaky way to do it, but what you could do is just write a coroutine entirely in the scheduler that just polls for I/O and then deals with that. So this is like a task that will actually run with all of the other tasks in the system. I don't know whether that's the best way to do it, but it's certainly a sneaky, subtle way to do it. And so what you do is you kind of instrument this scheduler where it's just like, okay, you have the two holding areas for reading and writing. You got this little I/O poller that just kind of checks to see whether data is available. You have this little I/O task which just kind of sits there and polls for I/O. And then what you do is you just write two system calls, read wait and write wait. And all these do, they actually do nothing whatsoever except take a task and put it into the waiting area. So what a read wait does is it essentially finds out what file number, like what's the file number of what you're waiting for. It drops you into the waiting area, and that's it. Write wait basically does the same thing. And the way that you use those is like this. Okay, so it's a really subtle change, but what you do is you write your echo server where before every single I/O operation, you just stick a read wait or a write wait. And so what this is going to, sort of the way that this is going to work is that this read wait thing, I'm going to say, okay, wait until there's something to read. And what that's going to do is it's going to go back into the scheduler and it's going to look at that socket and might say, well, okay, there's no data available on that. You go into the holding area. If data shows up, it will be taken out of the holding area and will actually come back to the statement right after the yield, which is receive some data. We're actually guaranteed that that's going to work, because we wouldn't have come back if there was no data to receive. So it's kind of a subtle execution here, but essentially every single I/O operation you just preface with these wait operations. And so if you run this sort of different version of that server, let me pull that up. So echo good here. I sort of have a different version of the OS, which kind of has those waiting areas. What you'll find is that, okay, so I have this server where it's, again, handle client, handle connections, and I've got the little alive task here. The only difference between the previous version is just putting these wait operations, read wait, write wait, read wait, and so forth. If I run that, what you're seeing is now this thing is, first of all, the server is just sitting there printing print on alive messages. So that's that task that was just basically printing some output that we can see that it's working. If I were to go over and telnet into this thing, it's basically processing that. So it's just echoing back what I typed. And then on top of that, it allows concurrent connection. So if I come over to another window and try to do the same thing, that operates as well. So this thing is basically now running like fully concurrent, like multiple socket connections plus like a task sort of printing output and so forth. So that might make your sort of brain sort of fry a little bit, but it's like basically putting those like I/O waiting things into the code, totally dealt with the fact that this thing is blocking. Let me just check on time there. All right, so that's a little wild that you can do that. If you don't like that I'm alive message, you can sort of take that out. So if you want to go to like a different version of the echo server, okay, so this is one that doesn't have the alive message in it. If you run that, okay, you get something a little bit more sane where it's just like server starting. If I start making connections to it and start typing at it, you'll see that, it basically says, okay, I got a connection from that port. If I go over to another window, and type that. I mean, I basically have two concurrent network connections operating there. And if you get to that point, you've basically created a multitasking OS. It might look a little bit weird, but if you think about what you can do, it's like, okay, I can run concurrent tasks, I can create, destroy, and wait for tasks, I can perform I/O operations, and I can write like a concurrent server basically on top of that. And if you look at sort of the code that you write, let me pull up the server code, this echo good thing. This code is pretty interesting in that it has like normal control flow, just almost exactly like what I would write with just a straight ahead like server using threads or something. You know, it's basically, you look at this, it's like, okay, server loop, create a socket, accept connections, and then launch some client. If you've done network programming, you've seen that kind of thing before. The client, it's basically just doing a bunch of reading and writing and, you know, like send operations. It's basically very standard sort of control flow. The only little catch is that you've got these yield statements stuck into the middle of it. So it's like, well, okay, those yields are a little bit, that looks a little bit weird. But what you've done here is built a server where there's no event callbacks. So if you've used something like async core or something like that, this is completely off on its own kind of angle of execution. And it's not using any threads, and it's not using any processing. So let me just pause there for a minute and see if anybody has any questions about that.
If there's no client connected, is the server basically running in a tight loop, yielding back and forth from the scheduler to the I'm alive task?
So the question is, if there's no clients connected, what is the scheduler doing? That's actually a great question. If there's nothing happening, so like let's say the server is asleep waiting for new connections. So if the server, if there's no connections, it's basically off somewhere waiting for some connection. If there's no clients, then I'm not running that. It turns out that if it's completely asleep, what the scheduler is running, and this is partly the reason why I did this trick, it's actually running the I/O task. And the I/O task is actually doing a little bit of a sneaky trick here. It's basically saying if the ready queue is completely empty, I'm just going to pull on the select until something happens. So basically it's going to do a blocking select there. And not, I mean, basically the only way that anything could even happen at this point, if everything's asleep, like server asleep, client asleep, nothing going on, the only way that anything interesting can happen is if some kind of I/O shows up. So that's kind of the what's happening there.
So that's truly asleep. It's waiting.
So at that point, it's actually literally like 0 CPU cycles just blocked somewhere.
Letting the real OS sleep.
Yeah, even the real OS is asleep on that. All right, so that might be, we haven't even gotten to the really brain frying part of this yet. Any other questions before we get to the ultimate sort of brain explosion in section 9 or whatever? So, yeah.
So this is going back a bit. The select call there is taking our dictionaries, right? It's the read waiting and write waiting dictionaries, which have task ID stuff and file descriptors in them. But what does it care about the task ID?
It doesn't.
And it just ignores it?
Yeah, it just ignores it. It turns out that the dictionaries actually map file descriptors to tasks. So the whole idea on read waiting and write waiting is that you're basically waiting for some kind of file I/O on some file descriptor.
So it's just going to look at the file descriptor.
And so it turns out select basically iterates over that. If you iterate over a dictionary, you just get the keys. So it's a little bit sneaky, but all right. So that's a little mind blowing. I was kind of hoping it would be a little mind blowing. I mean, you wouldn't want to come to a concurrency tutorial and not have any of that. The last little bit is just where it gets completely out of control. Major problem with coroutines is that you can't write subroutine. I've kind of glossed over that, but one thing to be aware of is that you can't, like one of the things that you might want to do is write like some kind of library function that maybe hides a bunch of details behind the scenes. If you're in a coroutine and you try to call like another coroutine as like a subroutine or a procedure, the whole thing basically falls on its face. Essentially, Python coroutines can only suspend from the top level. That, by the way, is something that stackless Python tries to get a hook on. If you've ever heard of stackless and want to know what one of the things that it does, it actually lets you do a whole bunch of like subroutine calls and then suspend a task from deep into the call stack. Since this isn't really a stackless tutorial, I'm not going to get into too much detail about that, but that's a big difference between like the standard Python implementation and something like that tool, is that in Python coroutines, you can't take that yield operation and push it into like deeper levels on the call stack. So it just the execution model just does not work out right. However, there is a way to create basically subroutines and functions with this. And in order to do it, you have to basically involve the task scheduler as an assistant on this. And you have to strictly stick to yield statements. And what the trick is it's basically something known as trampolining. And I'm going to show you sort of what this looks like. So let me pull up the. I'll have the code here. What I've got here is this add function is meant to be a subroutine as kind of like a suspendable coroutine, subroutine. Basically what it does is it takes two inputs, x and y, and yields the result x plus y. Looks a little weird. I mean, it's like, well, okay, it looks like a function, but it's doing some funny business with the yield statement. What you might want to do is in this main function, you could basically say like r equals yield add 2 and 2, print r, where this basically implements like a subroutine call. So you kind of have to look at this and think, wow, there's like some serious magic going on with the yield statement. But what's happening is this main is basically saying yield to the add function 2 and 2, and then this add function is going to take the two inputs and yield the result, and somehow the result is going to come back as this R. Turns out that you can do this in some scheduler code if you kind of coordinate things correctly. Basically, what you can do is you say m equals main, you basically run the main function, and the result that comes back, this m, is actually this other coroutine that you're going to execute. And then what you end up doing is sending it something to get it to execute. And then you take the result of that and you send it back into the original like main function. This is by far the most diabolical thing to wrap your brain around. But essentially there's this really bizarre control flow where essentially you run main, it comes back with the add, and then you go run the add as a separate task, take the result of that, and then route it back into the main. So you're sort of, so this is sort of what this trampoline thing is. I mean, it's basically main kind of jumps back into the scheduler, and then the scheduler jumps into the subroutine, and then that comes back and then back into main. So it's kind of this weird bounce kind of thing going on in the scheduler. Key point is that everything ends up routing through the scheduler when you do this. And it turns out that if you really go kind of to the ultimate limit on this, you can actually implement this in our OS as well. Essentially what you have to do is you have to essentially manually create your own call stack for subroutines. So we're going to do this entirely in the run method of a task. So you're basically going to implement your own call stack. What you're going to do is essentially when you run a task, you're going to check to see whether you got a system call or not. If you did, you're just going to defer that back to the original scheduler. If you got a coroutine back, you're going to end up doing this weird trampoline trick. Basically, you're going to build up a call stack, you're going to send in some value, and then you're going to end up doing kind of a subroutine call. There will be a quiz later, by the way. And then what you have to do is essentially, if some other value is coming back, you end up unwinding the call stack. So if you look at that, I'm going to just kind of leave that as an exercise for the reader to kind of wrap their brain around on the trip home. One of the things that you can do with that, and this is actually the cool part, is that you can actually start writing library functions that hide all of the low-level details of things. Like you can write like an accept operation that does the waiting and the accept. You can do like sends where you repeatedly send like things out of a buffer. You can do receive operations. Essentially what you can start doing is actually writing code where you can essentially do weird library calls that mimic exactly what you would do with like a normal sort of subroutine. This is a slightly different version of a Echo server that uses this, but if you look at this compared to the earlier code, let me just pull up this code that looks at that. In the code that we wrote earlier, I had to do like a read wait and a receive as like two different steps. In this new code, what you can do is essentially hide that, where you just say, I just want to receive. One step. So it's just like, okay, there's a library function. I'm going to sort of execute that as one operation. So you can essentially clean up a lot of the code that you write. If you take it one step further, actually some comments. If you're looking at this, you're saying this is absolutely insane at this point. I mean, it's basically you have like two types of callables in your program. It's like normal Python functions and methods, and then you have like suspendable coroutines. And it's like, it just looks bizarre. It's like you have yields everywhere, you have normal function calls. It's like you're basically in total sort of meltdown mode at this point. You can actually take this even further and write classes that mimic the interface of existing objects. This is basically a socket wrapper that implements the socket interface like accept, send, receive, close, and does all of this yield business inside of it. And here's a server that looks like that uses that. So this is an Echo server that is essentially doing yields and mimics the exact socket API, except for the yield statement. So, so there is some code that actually has that. Maybe I won't run it. Okay, yeah, we only have like 8 minutes left, but we're basically almost done. So there is some code that you can try to do that. But it's really interesting. I mean, it's basically, if you kind of make it through this level, you end up having like this sort of OS that almost exactly mimics like normal control flow that you would have in a multi-threaded application. So this is like traditional socket code over on the right, and this is the coroutine multitasking over on the left. Only difference between those two things is the yield statement. Otherwise, it's exactly the same. This is what you would write in Twisted, by the way. So it's I don't really have any comments on that specifically, but if you were to compare like this code to something like the async core or the Twisted library, it's totally different. I mean, basically with something like Twisted, you end up doing all sorts of event callbacks. It's a totally different way of programming. So I think that's pretty interesting. It's a little bit mind-blowing and mind-boggling to kind of get to this point, but it's really interesting that we were able to create like basically a fully multitasking like environment that mimics the same programming interface that you would end up using with like a thread program, other than that one yield statement kind of thrown onto things. All right, so now that we've reached the very, I did mention at the top that very that pinnacle there, the killer joke level. Did it cross over the killer joke, or did it? Okay, okay. So I'll have to adjust the chart there. Couple final words about some of this stuff. There's a lot of other things that you might explore with this whole setup. Possible with the scheduler that you could do things like inter-task communication, doing other kinds of handling of other, like blocking operations like databases and so forth. That would sort of take you well beyond the killer joke stage. I think as far as what to make of this tutorial, if anything, what I hope that people actually take away from it is that there's a lot more going on to generator functions in Python than Fibonacci numbers. Now, whether you would want to use all this stuff, I have no idea. But I think that a big takeaway is that there's just a lot of wild things happening. I mean, you can do Python, you can do processing pipes, you can do data flow, you can do all sorts of event handling. You can do this like cooperative, sort of multitasking thing. There's a lot of like really sort of cool stuff happening. Performance. I think this is like an area for somebody to explore. I didn't do a ton of benchmarking on this, but I actually did run a test putting this up against Twisted. So I don't know that this is the most appropriate test, but on a 4-core machine at my house, I just basically launched 3 sub-processes. I had each of them open up 300 socket connections with this server and then just blast like random 1024-byte messages at it as fast as it could do it. So, it's only one test, but this coroutine thing that I did was certainly competitive with what Twisted is doing. I'm not actually surprised by that because they're both kind of based on a select loop. It's just the overall like control flow is kind of different. It's a little bit interesting that programming with threads basically smoked them both. That thread benchmark was just done using the socket server library. So I actually ended up having like 900 threads running in some server, blasted both of them out of the water. I'm sure that I would suspect that there's some cutoff where maybe that isn't so, whether they're maybe more equal, but that's one thing to sort of explore. I'm not actually convinced that any of this is worth doing as an alternative to threads. I mentioned at the beginning I'm a little skeptical about this coroutine stuff, although I sort of tried my best to take it to the ultimate level that I could figure out before having a brain meltdown. This is really not clear to me. I mean, it's like threads in Python often get kind of a bad rap because of the GIL, but it's not actually clear to me as as a systems person that writing your own multitasker is somehow going to do better than what the OS does with thread scheduling. I think if anything, you're not going to beat the OS. So there is a little bit of a debate there. The other thing that is a little bit of an issue is that this multitasking stuff does not allow preemptible tasks. So one thing with threads is that if like a signal or anything comes in, they can basically preempt each other. When you start messing around with coroutines, if you block, you're basically out of luck at that point. I have a lot of experience with preemption at the moment. This is Thomas Beasley here. So I've had a ton of preemption while preparing this talk, where it's like about 7 o'clock in the morning, some intense wailing going on in the back room. So with threads, you don't face that. Another sort of risk is I'm still kind of wondering, like, why did coroutines kind of die in the 60s? I mean, it occurs to me that maybe there was a good reason why a lot of programming languages did not adopt this. I can't say for certain, but I mean, is it like Jason from Friday the 13th? You know, like you definitely don't want it coming back alive, or there's going to be some some horrible thing happen. I just don't know on that. And I think actually, if you come to the end of this tutorial, I think a reasonable person could actually claim that this coroutine business is way too clever to put into any kind of production software. I don't know. I mean, again, I don't know for certain, but as an experiment, you could bring my little multitasker into a code review and just sort of see what happens. See whether you're still employed afterward. Another thing to keep in mind is I think it's really important if you're going to do this stuff not to mix programming paradigms. So generator functions actually have many different uses in Python. I mean, they're used to feed the for loop, they're used to kind of receive messages, and they're also used for this kind of trap business and cooperative multitasking. I think it would be a really bad idea to try and write a generator that served more than one of those roles at any given time. I mean, that's just asking for asking for trouble. And then the final thing, I think if you are going to use this, probably a good idea to just keep it very under control. So, at least in the OS that I wrote, I was really trying hard to keep isolation between things, and that's maybe more of a personal preference, but I think if you are going to mess around with coroutines, I would definitely try to keep coroutines especially very well contained and isolated from other things. So I think what you would probably not want is like some horrendous tangled mess of coroutines, threads, and processing. And then some of the stuff that's using this is definitely not an exhaustive list, but if you kind of look at this this tutorial, you're saying, man, that was kind of wild. It's like doing multitasking with no threads and things like that. You should definitely go look at things like Stackless Python and PyPy. Those guys are like really into this sort of this thing, and actually at a whole sort of another level than what we're doing here. And there's a number of just sort of libraries that are kind of playing around with this. So this EventLit, I think that comes out of the Eve project, I think. There's a lot of this is coming out of like multiplayer games and sort of highly concurrent servers and so forth. There was a tutorial this morning on this Camellia that's also dealing with concurrency. It uses generators for part of how it works. And so those are some things to look at. So that's kind of the end of this tutorial. I hope at least I hope people maybe got some ideas from the course. Hope everyone's brain exploded just a little bit. I've sort of done my job doing that. And then just as a plug, I do teach Python classes, but they're not usually at quite this level of insanity. So that's the shameless plug there. So we're basically done. I can't believe that I actually finished those slides in the time allotted, but we're basically right at the end point in the class. So are there any questions or just comments on any of this stuff? I'm actually a little bit curious to know whether anybody thinks it's too insane to put into any kind of production use. Does anybody have any thoughts on that? Okay, so you're agreeing with me that it's so we have a question in the back.
So when you say don't mix paradigms, does that mean don't mix something, for example, I've got a system that uses multiprocessing, and I wrote my own scheduler and queuing system. If I were just to rewrite that portion using coroutines, would that be okay?
Probably be okay. I mean, my caution, I guess, more on the paradigms is just within the one generator function itself. Not trying to. What you shouldn't do is look at it, it's like, ooh, a generator. It's like you can do things with the for loop and you can send things and do this like, you wouldn't want to try and do too much in one generator function. I mean, it's like either use it for looping, use it for receiving, or do some kind of multitasking thing on it. But don't try to like do more than one of those in the same function though. Question all the way in the back.
Did you coin the trampoline nomenclature?
No, I think they use that in the PEP 342 actually. So I'm not exactly sure the origins of that, but they show an example of trampolining in the in PEP 342 actually. So yeah.
I think this answer or helps to answer the question. Gee, how can I make this program more complicated?
Okay, so yeah, if you need a way to make your program more complicated, this is definitely one way to do it. Or if you're thinking of a really diabolical job interview question, this could be a suitable domain. Another question in the middle.
Because you asked us, does this look too crazy to put into production? The question I'd sort of come back with is, well, it's worth considering if it gives us something we don't already have, right? So is there a fundamental win here that we don't get with threading or other models?
I think that's a really good question. The question is there a win here? I have like a gut feeling there's like something really interesting going on with this in terms of, there's a lot of interest right now in like how to deal with things like multi-core. There's a lot of people doing things with like Python in like embedded systems, writing servers that have like tons and tons of connections. I think there's like a potential that this could have something to offer in that area. The problem is I'll just admit that personally I don't feel like I have a really good handle on like the performance characteristics of some of this stuff, and like how I look at this and I say, well, this is kind of interesting, but as like an operating system person, I'm not actually convinced that I couldn't just do this with thread programming.
Well, for example, since you mentioned multi-core, and because earlier you mentioned the global interpreter lock, right? If this gave me a way to write a concurrent Python program that's scaled across multiple processors, that would be a big win, right?
Mm-hmm.
So does this have that? It doesn't seem like what you said today has that property, but do you think it has that potential?
I think it has that. I think it definitely has that potential. It's just whether anybody has explored it to that degree. I mean, I don't know. I mean, I think there's definitely a kernel of some very interesting stuff kind of churning around in the whole coroutine part of Python. I mean, it's not just this presentation, but these, even these third-party packages are kind of playing in the same space. But my sense is that there's just it's still a lot of churning going on. I mean, what's going to come out of it, I don't really know, but I'm actually really fascinated by this, this feature of Python, sort of like, where did this come from? How is this applicable to different, problems? Does it have anything to offer? I really don't know whether I have a good answer to that, but it interests me a lot. So, another question in the back.
Well, I'm just curious, maybe I'm misunderstanding this. It seems like you avoid some of the issues of locking and corruption from threads, avoid not having locks. So in what you've done here so far, right?
Right. Yeah. So one comment: if you stick to this just this coroutine business, if there's no threads in the system, then you don't need locks, because I mean you're not ever going to have that. One task is never going to get preempted behind the scenes to do that. So that would definitely be something that would be a win for this, is that you're not locking. The question is whether it can actually run fast enough, where it's like to have that win. Another question in the back.
I seem to remember when generators appeared, people referred to them as sort of partial coroutines, like they weren't true coroutines. And now we have coroutines. In the computer science literature, how does Python coroutines compare now? Would those folks say, okay, they are full-fledged coroutines?
So the question is, how do these compare to like full-fledged coroutines in computer science? I would say in the current implementation, there's still some limitations that kind of are a little bit warty on what we find in Python. One really serious limitation is that you can't yield from a function call. Like if you're in a coroutine and you start making a bunch of subroutine calls, in a lot of systems where they have sort of quote true coroutines, you can yield from down in the call stack. So we don't really get that. That's actually what that trampolining business is, kind of a hack to get around that. That's what stackless gives you, by the way, is that ability. Another sort of subtle difference in what Python does in other systems with coroutines, sometimes the sends are basically very asynchronous in a sense that, like, in the current Python coroutines, when you send something, control basically has to come back to where the send originated. There actually are systems where that does not actually take place. It's almost, you almost get into more of this sort of pure actor model kind of thing, where you can just fire off messages and it all operates really highly concurrently with not any particular order per se. So again, I'm not sure whether that's the best answer, but it's all right. Well, I hope people got something a little bit out of it. Mainly what I was trying to do is just kind of take this feature of Python and just run as far as possible with it, hoping to kind of shed light on sort of what it's about and different things that you can do with it. The multitasking stuff by far is the wildest aspect of it. Where that's going to go, I don't know, but I think it's really interesting, sort of how the code looks. I mean, I'm really interested in how it kind of compares with things like the twisted framework. I mean, it's like you're almost doing the same things that those guys are doing, but all completely off in this totally different execution style. I find that really kind of interesting. All right. Well, with that, I'll let everyone go to recover from the coroutines class. So I'd just like to thank you, everyone.